confirm that you're here? You can hear me from the chat. Can you hear me? Okay, great. I welcome you to week 2. Hope you had a wonderful time last week and you managed to use the Saturday and the Sunday for recap to make sure that we're on the same page. So as we are going to journey on in the remaining 5 days, before we start, we dive into what we're supposed to do today. I want to inquire from members in case, the participants, in case there's somebody who tried to do the assignment. I'm going to share again the assignment that we left. In case there is somebody or one or two who tried it out, we'll be glad to get the answers. And so in the last meeting, I'd left a simple exercise. This is the exercise that I left for a research study of your own topic. I guess most of us are having dissertations or are doing a research. State the topic, identify 2 study objectives, and then which data collection methods do you expect to use and why? And how would you compute your sample size? Can I see from participants, is there anybody who tried to do this exercise or you completely forgot? Anyone who can share with us? Anyone who tried, participants? Some are posting Valentine.
Helen, no one has raised their hand.
Okay. Since no one has raised their hand, then I'm just going to leave everything back to you in case you happen to get some time. Please try to see that you try this simple exercise and then share with us maybe tomorrow in case you'll be ready. It could be like the weekend was overlapped with many things. So for now, I'm going to hand over to Professor Susan to continue from here. Thank you all and welcome once again.
Possibly you can allow Lily, promoted Lily. If it is still okay, she can share.
Okay, Prof, I'm told Lily is willing to share. There's one. Okay.
Hello, can you get me, Dr. Helen?
Yes, please continue.
Okay, I've not really met like a PPT presentation on it, but from the questions I saw, actually I have my study which I want to currently do. So I want to probably present it to you and probably you can give me some more ideas. Is that possible?
If you can do it in 3 minutes.
Yes.
Okay.
So the topic of it is going to be on corporate green bonds. Corporate green bonds. So the objective, I would like to see how the stock market reacts to the issue of corporate green bonds. And I also like to look at if there is a source of greenwashing in the corporate green bond. So for the data collection, I'm going to be using secondary data. So I'll be using the Climate Bond Initiative. So I'll collect the data online on the Bluebeam. And how would you compute your sample size? Now, the sample size will depend on the number of companies I will see that have issued the green bonds. And I'll also be using like an event study analysis. That's why I wanted to also ask if you are going to be doing some like event study analysis during this seminar.
Are you going to cover that? Events analysis. Well, Lily, when time allows, we'll look at that. We are still following the program, but if all goes well, we will have a look at it. Maybe the other thing that you have to note in mind in case you're using secondary data, still you have to read the different details and see how that data was generated, because however much it's secondary, but usually there is already material on how they came up with that particular data, especially when it comes to sample size or the sampling procedures that were used. So it's a matter of getting that information, and then when you get to that section of sample size and sampling procedure, you try to rephrase what they did into your work. But you need to quote that, yes, I'm in this particular company, I'm going to get these numbers, but you're also supposed to indicate a reason why maybe you're going to pick 80, and then in the other company, you're going to pick 100. Like we discussed earlier, we talked about a probability proportional to size. In that particular case, it will come in because a company that will have many, let me call them observations, will have the greatest representation compared to the one that will have, for example, few observations. But it is workable, and that particular component has to be clearly explained.
Okay, thank you very much, Doctor.
You're welcome. Professor Susan, please continue. Thank you, Lily. I'd switched off David. Yes, I'm done. Maybe as Professor Susan says herself, kindly note that we put all the material in the Google Drive, all right? So all the content every day we keep uploading. So it's a matter of going back to the same link, click on it, and then you'll see day 6. Day 6 with today's date, it contains all the materials that we are going to use today. And we've also updated day 5 with the PowerPoint that Professor Susan used on Friday, which had some missing content that of the table that you wanted to see. So please check on the link and get the updated information. Thank you.
Good morning, participants. I hope you had a very good weekend, and welcome to day 1. I mean, should be day 6 of the training, but day 1 of this week. We are going to continue with statistical model ANOVA and post-ANOVA analysis. We had talked about ANOVA as a statistical technique that summarizes all the average values of a categorical variable. It's normally used to separate the amount of variability due to the treatment, and then we look at what remains, what is called a residual, and then we look at whether there are treatment effects on the experiment, on the response. Okay, so we had already gone through types of variables. We say that we have 2 major types, the qualitative, mainly categorical, and quantitative. Under qualitative, we saw nominal and ordinal. And then under quantitative, we have discrete and continuous, where discrete are obtained by counting, while continuous are obtained by measurement. Before we left, you gave me some questions, and one of the questions I saw is that I should talk about counts. Count data does not follow normal distribution. It follows a Poisson distribution, and Dr. Helen will talk about log linear regression, which we use when we find that our data follows a Poisson distribution. So log linear regression accounts for the type of distribution that is Poisson, while if your response is binary, meaning you have 2 responses, then we use logistic regression, which accounts for the binomial nature of the response. Then I also got other questions like, can you interpret the F value? Can we use the F value in interpretation? Yes, we can use the F value in interpretations, but you need to have an F distribution table, which I didn't download. So maybe as we go for a break, I'll download the F table and we can look at it. And when you use the F table or p-value, you get the same conclusions. So we say that in our example that we looked at, that if our p-value is small, you remember we looked at this example whereby we were comparing the growth of 4 different species, and we saw that the p-value was smaller than the significance level, which is 0.05. We also say that the significance level is the smallest probability that we assume that the null hypothesis is correct. And if we get anything lower than that significance level, then we have evidence to reject the null and conclude that not all means are equal, or at least one of the means is different. So we say that once we find a significant overall analysis of variance, then we don't end the story there. What we do is we go and do multiple pairwise comparisons. So looking at the questions, there's one more question, which model is suitable for a variable which is binary and then a dependent variable which is continuous? So if the response is binary and the dependent variable is continuous, as I've said, the response being binary does not follow normal distribution, it follows binomial distribution. So we model our data using logistic regression, even when the dependent variable is continuous. So Helen will cover that part maybe on Thursday or Wednesday, depending on how fast we move through the material. Okay. Okay, you're saying that my volume is low. Is it okay now? Can I see in the chat? Is volume okay? Okay. Okay. Okay, thank you very much. The volume is fine. Okay, so from there, I've just said that once we have a significant overall analysis of variance, then we are going to do pairwise comparisons. Okay? So under pairwise comparisons, we say that there are so many. Here we have least significant difference, which is called LSD. And then there's Turkey test, there's Dune. There are so many multiple pairwise comparisons that we can use to test whether there are differences in the means. So we've seen that overall, on average, when we add up all the values, there are significant differences, which we call the treatment effect. Now we want to know which particular mean is different from the other, and that's why we do treatment comparisons. And there are various types. We have the LSD, which is commonly used. We have Turkey test, we have Dune. And LSD here, under the LSD, we state a hypothesis, which says that if the absolute value of the two means, so if we take the mean of treatment I and subtract the mean of treatment J, if that absolute value, meaning you ignore the sign whether positive or negative, is greater than the cultured LSD, then those two means are different. So the formula for computing LSD is in the notes. We get a value from the t-distribution table. We use the mean square error from the analysis of variance table. Ri is the replicate for the ith treatment, and Rj is the replicate for the jth treatment. So the computer can give you this value. So you compare that value with the difference between two means. If the difference between two means is greater than the LSD, then we reject the H note, which says that the difference is equal to LSD, and conclude that the two means are significantly different. So when we do the practicals today, we are going to look at how we compute LSD in R. But those comparisons have problems in that our type 1 error, which Helen talked about, keeps on increasing on every comparison. For example, we have 4 treatments. We have 4 treatments, A, B, C, D. The number of comparisons is computed by using a simple formula, which is number of treatments, treatment levels, times the number of treatment levels minus 1 in bracket over 2. So here we have 4 times 3, which is 12, divided by 2, giving you 6 comparisons. So on comparison number 1, our significance level is going to be 0.05. When we go to comparison number 2, the significance level is going to increase from 0.05 maybe to 0.055. There is a formula if you want to compute those significance, I mean the type 1 errors as they change, there is a formula for that. So because of those problems, there is a solution to the problem. So in most cases, you are advised to plan your treatment comparisons or your questions, which we call pre-planned comparisons at proposal stage. And those pre-planned comparisons normally are independent of each other. But in these comparisons, you're looking at A minus B, then B minus C, then B minus D. You find that the information in A minus B there's some similarity between B minus C because you still have B in the same comparison. So the comparisons are not independent. So to solve this problem, we use what we call contrasts. So we are going to look at contrasts. I'll leave contrasts at that, and we look at them when we are doing the practical. It is more visible and more understandable when we are doing comparison. Other pairwise comparison rate, which try to control that problem of increasing type 1 error, are called Fisher's protected least significant difference. We have the Turkey's honestly significant difference, and in R it uses the Turkey HS function. Then the student new comparison, which uses the SNK test function in R. So all those comparisons are there. You can look them up if you really want to use them. But I've told you that still, even if they try to control the error rate, they don't really solve the problem. The only way we can solve the problem is to have pre-planned comparisons. For example, in this example we've analyzed where we are looking at different species and we are looking at how growth varies among the different species. In that experiment, we have species A and C are indigenous, while species B and D are exotic. So we can, at proposal stage, formulate our pre-planned comparisons. For example, do exotic species grow faster than the indigenous tree species? So what we are going to do under this comparison is we are going to get the average of the two species A and B and compare them with the average of B and D. So that is one comparison. Then the next comparison is, does growth among the exotic species differ? So in this comparison, we are only looking at the exotics. So we are going to get B minus D. Then we are also going to look at, does growth among the indigenous species differ? So in this case, we only look at the comparison of A and C. So those pre-planned comparisons are independent of each other. They don't share common information, and therefore they do not affect the type 1 error, or error rate does not increase. So how do we check this? When we come to, let me stop sharing this, and I'm going to share our document. So I'm going to share our document, an empty one. And what I want to do there is to show you how these comparisons vary. Sorry about that. Okay. Okay, let me use this same thing. Okay, so I wanted us to know how the comparisons work. So we have treatments A. Let me increase the font. So we have treatment A, we have treatment B, we have treatment C, and D. Okay, so I hope this is visible to everybody. Is it visible? Let me see in the chat. Is the screen visible? Okay, thank you very much. Okay, so in this example, we said A and C are indigenous, while B and D are exotic. Okay, so how do the pre-planned comparisons work? We wanted to know that on average, there is no difference between indigenous and exotic. So what we do, we get the average of A plus B plus C okay, divide by 2. Then we subtract in bracket B plus D divided by 2. So this is one comparison where we have the indigenous versus, this should be plus, indigenous versus the exotic. So that is comparison number 1. So then, when we are writing our contrast, we are going to take a half, because you can see that we've divided by 2. So we are going to formulate, in contrast, we formulate what we call contrast coefficients, which we use in R to specify the contrast line or command. So we will specify for A, it will have a coefficient which is a constant of 1 over 2. 1 over 2. So that is A, or the mean of A, into the mean of A, plus a half again into the mean of B, sorry, of C. Then we subtract again a half into the mean of B plus in bracket a half into the mean of D. So these ones, the halves are called contrast coefficients, as we can see here, and this is the first comparison. Then you can have a comparison. So let's have a comparison. Second comparison is between A and C. And we said A and C are indigenous. So in order to have that comparison, we are going to just have the difference between the two. So we'll have mean of A minus mean of C. So that's the comparison. The contrast coefficient will be 1 and minus 1. Now, how do we know that these comparisons are independent of each other? What we do is we take all the coefficients, for example, half, then multiply by 1, which is the coefficient here, because here we have only 1. 1 times 1 remains the same thing, and add them up. So we multiply, we get the product of the coefficients, add them up. If they add to 0, then those two comparisons are independent. And also to make sure that these coefficients are also independent of each other, we add them up. If they add to 0, for example, positive a half plus positive a half, we get 1, minus, these are negative all through, we get 0. So if we do the product of the coefficient and get 0, the two comparisons are independent. And if we also add them across and get 0, we know that those coefficients are independent. So when we find out that, we call those coefficients orthogonal. I hope you've heard of that term. We call them orthogonal, meaning independent of each other. They don't share any information. So even the third comparison, if we put the third comparison and multiply all through the coefficients, we will get 0 all through, indicating that our comparisons are independent of each other, and we can go ahead and present them in a publication because they are independent. And because of being independent, they don't increase the error rate. So that is, in simple terms, contrasts. So in the contrasts, we assign coefficients to each mean and then formulate comparisons. And comparisons come from pre-planned questions that were planned at proposal stage. We do not wake up, analyze our data, then we think of contrasts. In so doing, you're going to come up with contrasts which are not different from the pairwise comparisons. Okay, let me see in the chat. Any question about the contrasts? Okay, registration form for day 6 is going to be shared by Helen. She's going to get it from the IT specialists. They are formulating one. Okay. Can I repeat the contrast? We said that we had the pairwise comparison rate problem with the LSD, with the Fishers protected, with the Turkey, and all the tests, the treatment comparison rates, types that we normally use to test for the treatments. And we say that if you have 4 treatments, for example, if you look at the screen that I'm sharing, we have 4 treatments and the number of comparisons that you're going to get with those treatments. So I'm going to say number of comparisons is going to be equal to T number of treatments into T minus 1, everything divided by 2. So this gives us our comparison. So in this case, the number of comparisons that we'll get will be equal to 4, because we have 4 levels of treatments, or 4 treatments into 4 minus 1 in bracket, divide by 2. So we'll have 4 times 3 gives us 12. So our comparisons are going to be 6 comparisons. So these include A minus B, A minus B. Then we have A minus C, Then we'll have A minus D. Then we are going to have B minus C. Then we have B minus D. And the last one is going to be D minus C. So those are the comparisons, and you can see there are 6. Among these 4 treatments we get 6 comparisons. Now, at comparison number 1, our type 1 error, which is alpha significance level, I'll abbreviate, is equal to 0.05. Okay? Which we set. Now, when we go to 2, the significance level increases. Okay? So this significance level is greater. So alpha, the significance level that we use, will be larger. So it will be larger than 0.05. So as you go to 3, there is a problem with the type 1 error. It keeps on increasing. And remember, when type 1 error increases, if we are in a court and we are saying somebody did not murder and then the person is a murderer, for example, we are saying the person is a murderer and is not a murderer, and then the type 1 is increasing, that means you do not reject the null hypothesis. Yes, the null is what? Is true. Is false, sorry. You do not reject the null hypothesis, yet the null is true here. Sorry about that. So in that case, we are going to make wrong conclusions in court. So even in this case, if we are going to assume that the differences are significant, yet they shouldn't have been significant, because as you increase 0.05, the difference between A and B is likely to be statistically significant. And you're now going to pass on wrong information to the farmers and tell them that you can either plant A or B because they are giving us differences, or the difference is not significant. Okay? So when alpha increases, we are likely to reject the null, yet the null is false. Okay? So that is the problem we are trying to control with contrast. So what the contrast does, we plan our comparisons at the proposal stage. So instead of having 6 comparisons, you can see we have 6 comparisons: A minus B, A minus C, A minus D, and the rest. We can see that among these 3 comparisons, we share some information. There is similar information among A. In a comparison number 1, we have A. Comparison number 2, we also have A. So they are not independent of each other. The information here, the comparison, is not independent of each other. And that's what the contrast is trying to do. So the contrast, once we formulate our pre-planned comparisons beforehand, then we are going to have comparisons that are independent. Because here we say that in our example of species A and C are indigenous, while species B and D are exotic. So the first pre-planned comparison is that if we compare the average of exotic and the average of indigenous, are those averages statistically significant? So we are going to add up the average of A and C, divide by 2, minus B and D, divide by 2. So this is the first comparison. It's looking at overall, if we look at the indigenous species, is their growth rate different from the exotic species? That is the first comparison. The second comparison, we are looking at B and D. B and D are exotic species. So among the exotic species, are they different? So we are going to look at the average of, we are going to look at we are at comparison number 2. We are looking at A and C, and A and C are indigenous. So in that case, we want to find out whether among the exotics A and C there are differences. Okay, so we take A, the average of A minus the average of C. Now, when you look at this comparison, we are looking at only exotics. Here, we are looking at both the indigenous and the exotic. So we've got the average of the exotic, subtract the average of the indigenous. In comparison number 2, we are only looking at the exotic. In comparison number 3, we are looking at the indigenous. So those are the pre-planned questions where we are formulating contrast. And in the contrast, we are looking at, does A contrast C? Does B contrast D? That's what we are looking at. For us to be able to formulate contrast, we have to assign what they call coefficients, which are going to help us in computing our average, our differences. So in this case where we have A and C, we have assigned 1 times the average minus 1 times the average. So our coefficients, in this case, our coefficients are going to be 1, comma, and minus 1. So those are the two coefficients we are going to have. So here I put a comma. Those are the two coefficients we are going to use in our computations. So we are going to multiply the mean of A times coefficient A minus the mean of C times minus 1. Okay, so that gives us the second contrast. The third contrast, we are looking at the average. We are looking, are there differences in the indigenous? So we are looking at B and D. The average of B, is it different from the average of C? So those are the contrasts. And when you look at them, we can actually know whether they are independent by looking at these coefficients. So this is the second comparison. Let me put the first comparison. The first comparison, we are looking at a half, comma. We are also looking at a half into A, so that we don't get confused. A half into A, comma, then a half into B, into C. Then we have the ones which are negative, so we have minus a half into B, and then minus a half into D. Okay, so that is the first comparison. And why do we use halves? Because we are adding up the average of A and C and dividing by 2, and also adding up the average of B and D and dividing by 2, and then subtracting the two averages. Okay, so that's what we are using. So the second comparison, so this is the first comparison, this is the second comparison, and this one we have in bracket A and also in bracket C. The third comparison is also A into B, comma, minus 1 into D. Now, for that particular, when we have comparison number 2 where we have A minus C, because we are not looking at B and D, we award them coefficients 0. So we can complete here and put 0 and 0. Then even here, because we are not interested in the exotics, now we award them 0. Okay? It's like creating dummy variables, if you've heard of them. So we are awarding those coefficients for ease of computation of the differences between the exotics and also among the indigenous. So if we want to find out that these comparisons are independent, we take a product of the coefficients. So a half times 1, a half times 1 times 1, plus a half times minus 1 times minus 1, plus a half plus a half times 0 plus a half times 0 times 0. Add them up. If they add up to 0, then those comparisons are independent. What the statistician call it orthogonal, like they don't share any information among them. Okay? Okay, so let's go on. I think that is clear. Don't worry about the registration link. It will be posted anytime from now, unless if you just want to register and go away. Otherwise, you will get the registration link. Okay, so I'm going to stop sharing this and go to the screen again and share what we have. Okay, so there are some questions here. How can we do the same comparison in RCBD or factorial? As I've said, for any analysis of variance, the first thing we do, we check overall if there are significant treatment effect. And in case there are significant treatment effect, we want to find out which treatment is significant. So we can now use either the treatment pairwise comparison or contrast. So even for RCBD, because we have two factors, we can actually look at each factor independently of the other. Even in factorial, we have factors with levels. We can also look at the comparisons. We can use contrasts, okay, to look at, to compare among the factors. So it is not limited only to complete randomized design. To all analysis of variance tables, once they are significant, we go ahead and understand the contrast very well, then you do the contrast, okay? There's another question. I would like to know if you can do contrast when you are comparing 10 concentrations on a chemical on the response of animal. Yes, we can do comparisons, contrast on 10 concentrations. What, as I've said, pre-planned comparisons, those concentrations have meaning on them, attached to them, biological meanings. That's where we get the pre-planned comparisons. You might find that those concentrations are based on some literature. You must have read some literature for you to have the different concentrations. For example, you have a control. You can say that the first contrast is the control versus all of the all the 9 concentrations as your first contrast. Then the second contrast is you can have those contrasts, those concentrations which are low and those which are high. So that could be another pre-planned comparison. Then you can only compare only those which are low and only those which are high. Then find out if you formulate those as your pre-planned comparisons, attach your contrast coefficients, find out if the contrasts are independent, then go ahead to compute the contrast. And when you have a quantitative variable, normally the contrasts that we use are called linear contrast, quadratic contrast, or we can use the cubic contrast. So you can use those ones, but today we are not going to look at that. But you can use them, then run a regression on the contrast, and you will have results on those concentrations. And if you do not know how to do the linear and quadratic for those contrasts, then we can just award coefficients and run them the way you see we are going to run. Okay. So those are the questions I got in the chat. Please bring more questions, and Dr. Helen will be picking them, and I will answer them as we go ahead. So remember that we say that any statistical model has assumptions that make that model valid. Under the analysis of variance, we have assumptions. Okay, we assume that the explained variation, the noise that remains, is normally distributed, follows a normal distribution, have constant variance, and are independent. So how do we check those assumptions to know that our statistical model is valid? For constant variance, we use a plot of residuals versus fitted values. We are going to see this in R. For normality of residuals, we use a normal probability plot, as we shall see. And independence, we look at a plot of residuals versus experimental unit number. So if there is no pattern in the plot, then we know that our residuals are independent. So we are going through theory, but within 20 minutes we'll be turning to practicals, and whatever we've been talking about will become a reality. So people understand more when we are doing the practicals. So assuming we have two factors, then we are going to perform what we call a two-way analysis of variance. And in the factors, we have blocks and treatments. So this can be called a complete randomized block design. So my colleague, Dr. Thomas, talked about how you formulate those designs. That's why you see I'm just giving a model and going through the theory. So the model for a complete randomized design, block design, consists of the response, which is Yij. Mu is the overall mean over all the observed responses in the block, J, and treatment I. And rho, this sign here you see rho, is the block effect. And then tau, I, is the effect of the treatment on the response. E is epsilon, the Greek name epsilon is experimental error. So whatever variation remains is called experimental error. Experimental error is not error as in English. It is important in testing the treatment effect. So, but we try to minimize the experimental error, because if it is too big, then the treatment effect is going to result into being non-significant all that time. So we try to minimize the experimental error. So when you fit your treatment, look at your R squared to see how much variability has been explained. So if it's less than 70, then you know that your experimental error is big. And in that case, look at the treatment effect. And if it's non-significant, then probably it is because you have fewer replicates. Remember, the experimental error depends on the number of replicates you have. Okay, so Dr. Thomas talked about number of replicates. So if you have very few replicates, the experimental error is going to be bigger. Because the more the treatments are replicated across the experimental material or site, the smaller the experimental error. Okay, so this is the two-way ANOVA, and we are going to get an example in R. And I want us to first of all talk about the theory of designs with factorial treatment structure. Then from that, we are going to jump into the practicals, and whatever we've talked about is going to be done practically. Okay, so then let's look at the designs with factorial treatment structure. So sometimes we have factors, for example, fertilizer at 4 levels, but we also have species at 3 levels. And we want to perform an experiment. In these experiments, what we call the standard experiments, we normally have treatments only, maybe species only. Maybe we are looking at fertilizer only. But in factorial, it gives us an opportunity to look at the effect of treatment, the effect of fertilizer, the block effect, and then the interaction. So that is the aim of having factorial treatment structure. Okay, so we investigate the interaction and the main effects. Okay, so the ANOVA table, the dummy ANOVA table for a factorial treatment structure, we assume that in this experiment there are 2 factors. Treatment A has A levels, small a or lowercase a. Then treatment B has B levels, conducted in a complete randomized design. In this case, we do not have a block factor. Now, this ANOVA table is going to look like the way you see on the screen. We have the source of variation consisting of the treatment A, treatment B, the interaction AB, whatever remains is called the error, and the total. Now, degrees of freedom, sorry about that. Degrees of freedom for A is number of levels under A minus 1. Degrees of freedom for B is number of levels for B minus 1. The interaction, you multiply these two, A and B. So you have number of levels of A minus 1 into number of levels of B minus 1. That gives us the interaction. Then the error is AB, number of levels of A times number of levels of B, into the number of replicates minus 1. That gives us the error. And the total is N minus 1. Okay, that is the total variation. Okay, those are the degrees of freedom. Why do we need to know about this? When you perform any analysis, make sure you know what the software is giving you. Otherwise, you're going to present wrong results. And if anybody knows statistics on the panel, then you're going to get problems. I believe that most people know statistics when they sit on that panel, when you're defending, and they'll say, no, this is a wrong result. So we do not want you to present wrong results. Always check your results out. Don't just get excited, oh, they are significant, and you start jumping around when you don't know whether the results are correct. Sums of squares, we have formulas for this, but we'll not go through those formulas. Because if we go through formulas, then we will take a whole week talking about experimental design. Okay? So if you want formulas, we can always give you a reference and you can refer to them. But the most important thing is to know the degrees of freedom and the mean square error and the F ratio. Once you know how to compute these, which are very easy, then you will know how to check your output. The mean square error, we said, is the ratio of sums of squares divided by the degrees of freedom. So mean square for treatment A is sums of squares A divided by the degrees of freedom for A. The same applies to B and the interaction. The mean square for the interaction is sums of squares interaction divided by the degrees of freedom for interaction. The mean square error is sums of squares for error divided by the degrees of freedom for error. The F ratio is the ratio between the mean square of the treatment A over the mean square error. So I said that the experimental error is very important. It is the one we use to find out whether there is an effect of treatment A, which we call the main effect of treatment A. Is there an effect of treatment of A? Does treatment A affect the response? This is how we know, using the F ratio. Then, if you have the F table, you can actually interpret the F ratio. If this calculated F value is greater than the tabulated F ratio, then we have evidence to reject the null and conclude that there is no effect of treatment A. Now, treatment B, the F ratio for treatment B is the mean square B over the mean square error. Then the interaction, is there an interaction? What does interaction mean? Interaction means that does treatment A, the effect of treatment A on the response, does it vary at the different levels of B? So if we are looking at yield, does yield of the crops under treatment A vary when you vary treatment B? For example, if you increase the amount of fertilizer from no fertilizer to 0.5, is the yield at under treatment A, level 1, changing? If we increase the fertilizer to 1 gram, is the yield going to change for the different levels of A? That is an interaction. So we are going to look at what we call interaction plots, and they are going to give you a bigger picture and a clearer picture of what we call interaction and main effect. Okay? So when you have a factorial treatment structure and the interaction is significant at 0.05, if that is your significance level, then you don't need to interpret the main effect of A and B. You only look at the interaction because all the information in A and B is in the interaction. Okay? Now, if the interaction effect is non-significant, the p-value is greater than 0.05, you have no evidence to reject the null, which is saying no interaction effect, then we are going to interpret the main effects of A and B. We are going to look at the effect of treatment A on the response and also the effect of treatment B on the response. I repeat, if the interaction is significant, the p-value corresponding to interaction is smaller than 0.05. Our hypothesis is that there is no interaction effect on the response. And the alternative is that there is a significant interaction effect on the response. So in that case, we reject the null and conclude that actually the yield of the crops at A levels vary as you change levels of B. So meaning that the yield of the crops depends on the different levels of A and the different levels of B. The two factors are dependent. They depend on each other to increase the yield of the crops. Now, if you find that the p-value for the interaction AB is non-significant, meaning the p-value is greater than 0.05, then we can now look at the main effect of A and the main effect of B and interpret them. So in that case, when we are at the interaction, if the interaction is non-significant, then we go and do treatment pairwise comparisons for A and B. Now, if the interaction is significant, we construct what we call interaction plots, as we are going to see in the practicals. So hopefully that's clear. Let me see in the chat. Any query? Are we good to go? Can we continue? Okay, thank you very much. Great. Okay, let's continue. So probably that is the end. Okay. Okay, so we've already said factorial permits us to answer several questions with little added labor. So what do I mean by little added labor? The material you use for conducting a CRD is the same material you use for conducting a factorial treatment structure, a design with a factorial treatment structure. Remember, it is a CRD with a factorial treatment structure. So when you're writing your proposal, you're going to say, I'm going to conduct a CRD, complete randomized design, but because your treatments have levels, you have a factorial treatment structure where A has 4 levels and B has 3 levels. So that is your design. So the factorial treatment structure increases precision because when we look at the interaction, we are looking at the effect of treatment A over the levels of B. And we're also looking at the effect of B over the levels of treatment A. So by doing that, we are increasing the precision. What is a factor? A factor is a treatment variable which is varied at will by the experimenter. So these factors are fixed because you vary them at will, and the number of factors depend on the resources you have. Now remember, in a factorial treatment structure, if you have too many levels, for example, 7 levels, and treatment B has 8 levels, then the interpretation is going to become too difficult. So the number of levels also matter. So if you have too many levels of A and too many levels of B, then you're going to have, remember in the interaction, you have 2-way, 3-way, 4-way, and the interpretation is going to become difficult. Now, a factor can be quantitative or qualitative. Qualitative like species type, quantitative like amount of fertilizer. Now, when you are performing an experiment in the field, the treatments under factorial treatment structure are a treatment combination of A level and B level. So in each experimental unit, you receive one level of each factor. For example, you receive A1 and B1 in experimental unit 1. Experimental unit 2, you can receive A1 and B2. Okay? Remember, you're going to have, if you have 4 by 4, that means you're going to have 16 treatment combinations. And then randomize them to the experimental units. So each experimental unit is going to receive one treatment combination. Do not separate them, because the main aim of conducting a design or coming up with a design with a factorial treatment structure is to investigate the interaction. And you cannot investigate an interaction if the treatments are separated. One is in experimental unit number 1 and another one is in 2. We can't assess the interaction. So you have to place them in the same experimental unit. For example, you have species A and fertilizer 0 grams. That is one experimental unit. That's what it is receiving. Then experimental unit number 2 is going to have species B and fertilizer level maybe 0.5. Okay? So the ones that you replicate are the treatment combinations. So if you have 16 treatment combinations, you replicate them 3 times. That means we are going to have 48 experimental units. Okay. Okay, so let me see. I have one question here. If effect of A and B and the interaction are all significant, do you discuss only the interaction? Yes, that's what I said. And if not, and if A and B are significant, but the interaction is not significant, then we look at the main effect of A and main effect of B and do treatment pairwise comparison. If the interaction is significant, we construct an interaction plot, which is going to show us at what level of A is B performing best. At what level are we going to tell the farmers what combination is the best? That's what the interaction plot shows us. Okay, as we are going to say. Okay, so some form of expression expressing the factorial structure. So sometimes you have levels, similar levels, and maybe 3 factors. So the 3 factors all have 2 levels. So for example, we have 2 to the power n, where 2 denotes the number of levels and n denotes the factors. So if we have 3 factors, we are going to have 2 to the power 3, giving us 8 treatment combinations. And if you replicate them r times or 2 times, you're going to have 16 experimental units. Okay? So sometimes if the levels are similar, then you use 2 to the power n, where n is the number of factors. If the levels are not similar, for example, treatment A has 3 levels, treatment B has 4 levels, it's going to be a 3 by 4 factorial treatment structure. Okay, so that's when you're writing your proposal or when you're discussing the part of design in your write-up. Okay. So here it's just explaining what interaction means. Interaction comparison investigates whether the effect of one factor is the same at different levels of the other. And I've just said, if the interaction is significant, then clearly the effect of one factor is different at the different levels of the other factor. In this situation, the interpretation of the main effect of a factor averaged over a factor is misleading. So what I'm saying that when the interaction is significant, just look at the interaction. It is good enough. If the interaction is non-significant, then let's look at the factors separately. Okay, so split plot will be looked at. My colleague, Dr. Thomas, is going to talk about split plot and then incomplete block design. So we just shared the roles. Don't worry, you're not going to miss anything. If there is no question, if I can look in the chat, we want to turn to R and do it practically, okay? And see what happens practically. You know, when you see things, when you see by doing, you learn more than hearing somebody talking, okay? Last Sunday, I was hearing somebody saying that when you show children a video, they learn everything. No, when there is no interaction, it does not mean that the design does not have a factorial treatment structure. It still has a factorial treatment structure because practical, actually, that's what you did. You applied the two treatments in each experimental. You applied the different levels of treatment in each experimental unit. Okay, so design-wise, it has a factorial treatment structure, but the interaction has no effect on the response. So then we just need to do what? To go ahead and interpret the individual factors. Okay? Okay. So please share the attendance list link. Dr. Helen is going to send it. Don't worry about registration. You're going to register. Just pay attention so that we share this knowledge and benefit from this presentation. Okay, let us go to R. So please turn to R. There is a script called ANOVA. That is what we are going to use. We are going to use ANOVA to do what we've been talking about practically. So within a few minutes, Helen will be posting the link, okay? So I'm going to stop sharing this and share R. How do we go to R? Okay, just escape, hit escape, and then open R. So you can actually just open the R script and R will open, or R Studio will open. Okay, there we are. Yeah. I have said that if you have so many factors, then the advantage of factorial treatment structure really breaks down because you're going to have problems interpreting. For if you have an interaction of A times B times C times D times E, how are you going to interpret it? So somehow we have to use, we have to put in, you know, think about what you're doing and how you're going to interpret it. Okay. So we are in this script called ANOVA, and I hope everybody now is in R. Let me see in the chat if we are all in R. Are we in R now? Okay, can I see yeses flying around? Okay, great. I don't know what the B means. Maybe you're answering somebody. Okay, I haven't. Please turn to R. Not yet. In 1 minute, can you please go to R so that we can. And remember that we need to set our directorate to the folder where you saved the data sets, where you saved the script. Where is the script? Upload it from the Google link. The script is there. It was sent last week, day 5, isn't it? Yes, Helen confirms that day 5 has the ANOVA script. Okay, so please go to the Google link. I don't have the software, that means you've not been around, but you can still go to day 1 in the Google link and get the instructions on how to install R. If you can do it very fast, then you're going to follow. And Helen has just posted the link, the registration link, and the folder, the Google link. So please, you can register for day 6. the registration link has been sent. Okay, so I assume now we are all at the same level. The ground is leveled. Okay. Our politicians here in Uganda always say the ground is not leveled. I don't know how they level the ground. I hope we are the same ground now. Okay. Okay. So remember, we have to load our packages so that we can run R. Don't ask me why. That is how it was made. Probably somebody is going to come up with a program. Maybe you. In that we don't need to load the library every time we run R. So you can make that your project. And okay, so if you are in ANOVA, just select those packages and load them. It is very easy, just like you're seeing. I hope you're able to see. If you're not able to see, then I'm going to go into view and zoom in. Okay, try to make it a bit wider. So zoom in. Okay, so I am selecting all of these. I don't want Ara to tell me that they don't have. So under this, we have things like Agricola, DUE, HMISC, that we require even for regression. DUE is for design. Agricola is also for design. So all those ones, include them, and I am assuming you installed them. I remember my colleague Thomas talked about Agricola, and if it didn't install, then you need to update your R. If you do not have DUE, also install it, but you can actually put for example, if I put in front of library DUE, if I put hash, then it's not going to say that it doesn't exist. But we may need it, so install it in case you do not have DUE. Just put install. We can go here. Let me just copy DUE. So if you write install, and R is very good, it will brings you what you want. Then you put it in inverted commas. Okay. So that is, I've already installed, but if you've not installed, just write this command, install packages in bracket, DUE, inverted commas, then click run. Once it runs, then you're good to go. It doesn't take even 5 minutes, it takes like 2 minutes. Then let's load the packages we need to use. So run. So it takes like also, you see it has taken less than a minute. Then after loading the packages, you have to set the directorate where you stored your R script and data sets. Okay, so I'm going to go through this session, set working directorate, choose the directorate. Session set working directorate, choose. Mine is in practice. So you browse over your documents and look for where your folder is, where you've stored your information for R for today. That is the folder you're going to use. And once it is under the folder, highlighted blue, then click open. So if you look in the console, you will see that has already given you the command if next time you don't want to use the menu to set your directorate. So I'm assuming you've set directorate. Let's go ahead. So in this exercise of analysis of variance one way, we are going to use the same data we've been discussing in our notes. And the data set is called forest.csv. We are going to import that data set. You can always practice and write the commands, or you can just run what I have. So put the cursor anywhere and run the first command, which says forest assign read. So I'm reading, importing it from Excel and bringing it into R. Then when you see the name of the object forest, it will, if you run it, it brings all the data set you have. So if you go to the console, you will see the names of the data set. It has 2 variables and 24 observations. We have growth and species. Okay, so I'm assuming you've done that. We can look at the structure of the data by using str in bracket, the object which is forest where our data is, and just run the 3rd line, which is line 23. And it says, when we run the structure, it says that growth is numeric and species is a character. So for us to be able to use species, we have to change it to a factor. So in this command, line 24, we assign an object called species, and the function is factor. You can use as factor. So in that case, you will have forest $sign species assigned as dot factor, forest $sign species. So here we are just using factor. You can use whatever you are comfortable with. So if you run, you find that it has changed to a factor. And if you want to check whether it is being converted to a factor, use class. Use a function class. So click class, and you see that in the console, it returns factor, meaning it has changed our species character into a factor. So let's summarize. Remember, when you get a data set, you want to do analysis. The first thing we do is to do our exploratory data analysis. So we are going to summarize growth overall by using the command summary or function summary. So this gives us overall, what is the average growth rate? It's 26. Oh, I'm told that you're still importing the data. Oh my goodness, sorry about that. I was moving, knowing that you know these things already. Let me see in the chat. Okay, I can see. Okay, I'm giving you, oh, somebody says we are together. Are we all together? Let me see in the chat. Where are we? Not yet, no. Yes, I have imported. Proceed. No. Okay, together. Working directory empty, meaning that you have a different one. Okay, installing package too long. Okay, we are together, not yet. Okay, on average, we will just do a simple recap. Okay, so we are importing the data again. And everybody go to line, says forest is the object I'm assigning to that command of reading my data from CSV. So when you run that and you don't see any query in the console, then run the next command, which is line 22. It's just to see the data set you can either use view head, but now if you just print the object, it brings everything. So I say that you can actually look at how the variables have been written. Okay, in the environment, it shows that forest object has 24 observations and 2 variables, growth and species. So are we at that same stage with me? Can I see in the chat? He says he couldn't import. Are you using the same command? Helen will help you with that. Helen, help that person who cannot import. Probably probably, how can you enter the training in the middle? that answer is yours. You will answer yourself. But you can follow what we are doing. Since you have the script, just go into the script and follow. Which folder? The folder has to be. Yes. If you have a problem, please post your problem in Q&A. It stays longer than in the chat, okay? So Helen will be able to help you and my colleague Thomas, okay? So somebody has just pasted a long, don't mind about HMSIC. We will not use it now. There is no package Agricola, you haven't installed it. So use the install command, please. Please use the install command. Who is this one? I'm giving you people 5 minutes to sort yourselves out, because now I can only show you the command for install. So at the beginning, we said if you don't have a package called Due, let me also write another command, install, for those who don't have these packages. If you write install, R brings you that command, and then in bracket you write Agricola. Agri. Then it comes up, you see. If you do not have, which other package don't we have? Okay, assuming you don't have those two, just write the 2 lines, install.packages in inverted commas Due, or install.packages in inverted comma Agricola. So run them and then you load the libraries. So if you want to, you load the packages, sorry about that, using library function. If you want to load the packages, you write library in bracket, the name of the package. We've already done that. So for those who are behind, highlight the packages. I'm going through it so that you people. So once you hit run, because I've already loaded them, I'm not going to load the second time, then they are all going to run. If anything, and you have a query that there's no package called maybe Agricoli, that means you have not installed it. Then what we are, number 3 is to set the directorate. Now, where you are storing your information for this training, that is the folder we are using. Mine is different from yours because the computers are different. The folder you have on your computer, where you've put all the script ANOVA, is where the data should be. So pick the data wherever you've put it in the same folder where the script ANOVA is, and set that folder as your working directorate. So how do we do that? You go to session, we go to session, so let me see. We go to session. Okay. I have a question here. Let me first of all deal with this, then I answer that question. So if you're setting your directorate, go to session, set working directorate, choose working directorate. Then you browse in your document where that directorate is, click on it and click open. That's how we set our directorate. Now, some people are writing the wrong spelling for the packages. That's why they don't install. So if you write Agricoli without E, it is going to say it doesn't exist. So make sure you write the correct package name. And if you're writing the command install, you must have inverted commas on the word, the name of the package. Are we at the same stage now? Can we go ahead? Maybe we shouldn't have gone for the weekend. It seems we shouldn't have had the weekend because the weekend has disorganized a bit. Okay. Somebody is saying hangover. Okay, so let's go ahead because we want also to get some information from Dr. Thomas. So if you set your working directory to where your data set are, look at line 23 of that script. We are going to import our data set called forest.csv. The object is forest, then we assign using the read command or function. So let me run that. When you run it, you will see in the console blue information. If you see red, don't panic. Just read the error. You know, when I was a student, whenever I would see an error in SAS or GeneStat, I would start panicking, you know, and when you start panicking, everything vanishes and you can't concentrate. You don't even know how to interpret the error. So what you should do, if you see any red in the console, breathe in and out and read the error and you'll be able to understand the error and go on. If you don't understand the error, highlight, select the error, paste it in Google, and the Google Assistant is going to tell you how to solve that problem. Because after the 6 days we are training, you will be by yourself. And I don't say that it is good for you. No, I am saying that you need to learn to deal with the errors. Don't panic when you see a red error coming up, a warning coming up. So then the next thing is to see what is in our data set. So I said forest. Sometimes you write head in bracket forest so that you can see the first 6 rows of your data set. View, you will view the whole data set. So when you write forest, it's also another way of saying I want to view what is in my data set. So this data set, if you look at the environment on your right hand in RStudio, it is going to say forest has 24 observations and 2 variables, growth and species. We want to see the structure. What is in that data set? We use str in bracket forest. So when we run that, it says, if we look in the console, it says growth is numeric and species is a character. We want to change species to a factor so that we are able to use it in further analysis. So then we assign an object species and use the function factor to be able to convert it to a factor. So line 25 has that command. So when you run that, it is changed to a factor. So for us to check whether it has been converted to a factor, use the class command. And when you run it in the console, you see that has been changed to species, has been changed to a factor. And we say the first thing we do for any data set is we do descriptive statistics or exploratory data analysis. So we summarize our data. So let's use the summary command. So at this stage, are we together? Can I proceed? Okay, great. I'm going to go on. So if we look at the console, we will see that the results indicate that the minimum growth is 11.45. The median is 26.16. The mean is 26.82, almost close to the median. The maximum is 43.32. That's the maximum growth. But we want to know for species A, B, C, what is the average growth? So that's what we want to know. And we can do that differently. I'm saying that we can construct a box plot. And it is a recap of what we did in our exploratory data analysis. For us to do that, we use the library dplyr, which we've already installed. And the command, we apply these percentages, they are called a pipe. Just like the water goes through a pipe, we want the command to go through in one go. So we call our object forest and group the data by species and then summarize growth. And what we want to summarize is the mean growth. So we run that whole command and it gives us in the console, if you're in the console, you see that the species with the highest growth rate is species B with 37.4. The one with the lowest is species A with 20.5. Okay? And if you look at the magnitude of these species, we see that A and C are in the same range, 20.5, 19.5. So they are likely not to be significantly different. But A and B are not in the same range, so they are likely to be significant. So let's construct a box plot for our data. So we already know how to do that. We are not going to spend a lot of time on that. And there are two ways. You can use a ggplot or you can use the function box plot. So if I also run the one of gg and then I'm going to explain, I'm zooming in and then stop sharing this. I want to share the results of the box plot. So I assume that everybody can view the box plot. Can you view the box plot? Can I see in the chat? Is it visible? Okay, thank you very much. That is very good. So we can see that the same information that we had in a table is being presented here. We see that the species with the lowest growth rate is species A. Also C has a lower growth rate. The one with the highest growth rate is B. You can see it has the highest median. The middle value here is the median. We talked about this in the exploratory data analysis. So box plots can be used to compare between groups. So you can see we have 4 species and we can look at the different medians and be able to tell which one has the highest median, which one has the lowest. We can also know from this pictorial diagram which means are different from the other. For example, B is different from A as well as from C and D. But A and B, if you look at the magnitude, they don't look different. Okay? Also, D is different from C and also from A. Okay? So if we can also look at the distribution, these ones I'll leave them for you since we've already talked about distribution. So let's go and look at another, go back to R. Okay, so now we've seen that there are differences. The box plot indicates that among the species, we have different growth rates. So we'd like to use the analysis of variance and find out overall, are there differences? Does growth vary with the species? Are there differences among the different species as far as growth is concerned? So we can now perform our analysis of variance. Now, if we had 2 groups, species A and B, we would perform a 2 sample t-test. But now because there are more than 2, we are going to perform an analysis of variance. And because we have 1 factor, we are going to perform a one-way analysis of variance using a function LM, meaning linear model. So what we start with is the structure. We check the structure again. It hasn't changed. So we convert species to a factor. And then the object I'm assigning to my command LM is called status.ANOVA. So this is just an object and the function is LM. Growth is a function of species and the data is called forest. So let's run that command, which is line 48. We don't see anything, so we want to see the results of status ANOVA. Just run status ANOVA. And what is it giving us? The coefficients only, not the anisovariance table. So we are going to put ANOVA in bracket, the model, this one, GLM, for us to be able to get the anisovariance table. So you run that, it gives us the anisovariance table. So in the console, let everybody look at the console. Okay? We have the anisovariance table, which we had in our notes. And if we look at the anisovariance table, we have degrees of freedom. We can check. We had 4 species minus 1. We have 3 degrees of freedom. That is correct. And we have 24 observations. The residual degrees of freedom is number of observations minus the number of treatments. So 24 minus 4 gives us 20. That is also correct. So let's look at the p-value. We could look at the f-value if we had the f-table. And when you use the f-table and you want to look up the value, corresponding value at 5%, you use the degrees of freedom. Numerator becomes 3 and denominator 20. And the value intersecting those two values at 5% is what you compare with this tabulated value. Okay? But for simplicity, let's look at the p-value. We have stated that our significance level will be 5%. Now, our p-value is 0.000467, meaning that the chance that the null, which null was that there's no species effect on the growth, or growth does not vary among the species, and then the alternative is that there is a species effect on growth, or growth varies among the species. So because now the probability that the null is assumed to be correct is very low, it's not even there. Therefore, we reject the null and conclude that growth varies among the species. So overall, there is a significant species effect. I'm just changing the words, using different words. You can pick whatever is easier for you. Overall, there is a species effect, or growth significantly varies with species. Okay? Then from there, if that is what we've observed, we go and do a treatment pairwise comparison. So is that okay in the chat? Can I see in the chat? Okay. Yes, there's a difference. The results are not different, but they are just different functions. So there's a question in the chat. Is LM different from AOV? LM, the results are the same, but the functions are different. So let's go and run the alternative. If you don't want to use LM, you can use AOV as the function for getting the analysis of variance table. So I have named the species, the object is species without S, and we have AOV, growth is a function of species, data is forest. So let's run that, and summary species, we get the same results as above, and the interpretation is still the same. So I've given you 2 ways you can use, whichever is easier for you, gives the same results. So let's go and do multiple comparison tests, the post hoc tests, using LSD. That is line 61 in the script. So LS is the object, the function is lsd.test, and then we bring the model. The object which we used in ANOVA or LM is what we are writing. Here in ANOVA, I used species without S, comma, then I put in bracket, in inverted comma, species. That's what I want to test. That is the categorical variable I want to test. So if we run line 63 and then run our object, then we will see the values, the mean values for each. And what LSD does, it assigns letters. Now, have you seen in some manuscripts whereby they say letters, similar letters or similar subscripts on the means indicate that those means are statistically not significant at 5%. This is what LSD has done in R. It has assigned those letters. You can see that B and D have different letters, meaning that the mean of D is different from the mean of B. When we look at A and C, they have similar letters, meaning the difference between A and C is not statistically significant at 5%. So that's why they have similar letters. When we look at B and A, the superscripts they have is small a and small c. Now, because A is different from C, the mean of B is significantly different from the mean of A. We can even say the mean of B is significantly higher than the mean of A. You can see the magnitude. B is 37.4 and A is 20.49. Okay? So that's how the data, you can actually take this in a Word document and put these superscripts on your means and also assign some standard errors and write around them, okay, in your manuscript or your project. Okay, so from there we can also draw a bar graph and also maybe put error bars. So let's run this bar graph here. You can see that in the Y limit, we have put the minimum value and maximum as 40. You can change these actually. You can put 50, you can put 60. So if we change and put 50 and run again, we shall see that the box plots are reducing depending on the values of the means. Yeah. So if I zoom in that particular one, it is the same information in LSD. It has been transferred into a bar graph. So these are bar graph of the average growth rate, and we can see that B and D are significantly different because these letters are different. A and C, oh, let me share, sorry about that. I'm sorry, I had forgotten to share. So let me share the graph. Okay, can you see the graph? Is it visible? Okay, so the same information we had in our LSD in the table can be shown in a form of a bar graph. So under the bar graph, we can say bar graphs with similar lowercase letters are not statistically significant at 5%. So A and C are not different. You can see B and D are different. Okay? So same information presented differently. Don't present the graph and also the table of LSD. Present one of them in your manuscript or your project. Species is the model, is the object which is assigned, and then species is the name of the different categories of species in the data set. Okay, so I just used an object species to give it to the command AOV so that I can run that command. Instead of giving it, we can give it a different name. So let's go a little bit back. And ANOVA, instead of species, I am going to give it, oops. So here we are in the script. Somebody saying that, is there a difference between species and species? In this same line 53, species without an S is an object. So you can actually call it something else. You can remove and call it SP. Or you can call it SY. That is the name of what? Of the object. Okay? So I just, for ease, called it species. And then you run, you get the same thing. Okay? Okay, so let's go on. Now, there are different types of tests you can do. We said you can do Turkey-Honest difference. You can do, there's another one. So the Turkey-Honest difference entails you to run the model again. You can say I have X's in my, I have to run this again because it is saying they don't recognize species. And then run the summary, it is okay. So let me go down here. It has some, it is saying there is a problem in this. So let's run this and see which problem is there. It is okay, although it is complaining. Okay, so this is the line of commands you can you can use to run a Turkey test. So use the species under AOV. It is the object containing this model. And then species.turkey is an object you are assigning to the Turkey test. So run it. And then you run species.turkey. It gives you the pairwise comparisons. You can see in Turkey test, it is showing as A minus, all the 6 comparisons are being shown here, including the differences and the corresponding p-values. Okay? So in your project, you don't want to present all these things. You can actually present the table of the LSD as I showed you. Have the means and then put the superscripts and say means of the same letters are not significantly different. Okay, so let's go and there's also another way you can run the Turkey test. You can use HDS, Turkey-Honest significant difference, and that one is under library multi-comp view. So we don't want to have so many libraries. So that one I'll skip and go to pre-planned comparisons. You can run it at your free time. It's the same data information you're going to get. When you get the problem of figure margins, go to view and zoom out twice. That means that the window where the graph is supposed to be seen has reduced in size because you've expanded the RStudio window and the console. So you go and zoom out twice and you'll be able to solve that problem of figure margins. Okay, it's not a big problem. Okay, so we have pre-planned comparisons, the contrasts. I want us to have a feel of what contrasts are in R. In order for us to run contrasts, I have said that we install package called G models. So please just run that particular command. It won't take long. Just run it the way you see it. It is line 82. Run and then load. So I'm going to run because I already have it on my computer. I'm just going to load it. So I've loaded it and it is running. So once you run it, I'm giving you 1 minute. Install Gmodels to be able to do contrasts. Okay. Okay. So can we go ahead? Can we go on? Everybody has. Okay. Thank you. Okay. Okay, so everybody's fine. Now, we remember we had three pre-planned comparisons. We were looking at exotics different from indigenous species. The second comparison was, are there differences in the exotic? The third one, are there differences among the indigenous species? So we have 4 comparisons, and we want to compare. We said A and C are indigenous, while B and D are exotic, if I remember very well. So you see, we've in R, we assign these coefficients. You can see them to tell R that you're getting the average of exotic minus the average of indigenous. And is there a difference in the average? So we are getting A and C. So A plus C over 2, then minus B plus D over 2. So the average of the exotic minus the average of the indigenous. Are there differences? Overall, if we look at the performance of exotic, is it different from the performance of exotic? So that's the line we are running. It is fit.contrast. Species is the object of the model we run in AOV, and species, that is, those are the categorical variable we would like to contrast. So let's run. And when you look in the console, it has run the command fit contrast, and it has estimated the difference between A and B and D minus A and C. Okay? So let me copy this and take it to maybe a Word document, isn't it? Maybe it makes it more visible. I don't know. Maybe is it visible? Can we go ahead? I have the estimate of the difference, that is the contrast difference, the standard error, the t-value, and the corresponding p-value. So it is contrasting A and C minus B and D. And the difference is negative, meaning that the average of A and C is smaller than B and D. So the exotics grow at a slow rate compared to the indigenous because the average is negative. And that difference is significant at 5% because this p-value is 8.3744 times 10 to the power minus 7. So it is smaller than 0.005. So overall, the exotics grow significantly slower compared to the indigenous species. That is contrast number 1. Then contrast number 2. Are there differences among the exotics? So let's run. Among the exotics, the p-value is 0.7. It is saying among the exotic, the growth rate is not statistically different. So if you want to choose among the exotic, you can grow any of them. These 2 exotics are the one that has 20 and 19 point something. So you can see the p-value is 0.72. It is bigger than 0.05. The difference is not significant. Then among the indigenous, are there differences in the growth rate? Yes, it says the p-value is 0.013. Among the 2 exotics, B and D, there are differences. Now the mean difference is negative, meaning that B, you see, we are saying 1 minus D minus B, meaning B has a higher mean average growth rate compared to D, as we saw in our output. Okay? So that's how we run the contrast. Can I see in the chart? Is everything okay? I'm almost lost from line 83. No. So if you say no, some are saying no, what is not okay? Fairly. Yes, it is okay. Okay, so what I'm going to do, the commands are okay. It is the output. So what I'm going to do is I'm going to copy this, take it to a Word document, also copy the means because we want to look at those means and make it more lively, I think, when we have those means. Okay, there we are. So okay, I'll stop sharing and I would like to copy the means. It's not coming up. Okay, just a minute. Oh, give me a minute. I need to sort this out. Okay, ladies and gentlemen, I'm back. Okay, I wanted us to take it to Word document, but I need to have converted into a PDF, and it's going to be a bit longer. I wanted us to take the output so that you can understand. So I had complaints that people had gotten lost from the contrast part. Okay, from 83, line 83, that we got lost. So I'm assuming that everybody installed a package, G models, and we wanted to do the contrast. Now, I remember in the Word document, which we were looking at, we explained the coefficients. The same coefficients are the ones that I'm bringing here. So if I can do that and write around this, you can see my cursor. Here I have A. So A, and then here, so this is species A, this is species B, this is species C, and this is D. In our experiment, we know that A and C are exotic species, and then B and D are indigenous, and that is how it has been arranged. What we want to do is we are running a pre-planned comparison where we are saying that are there differences between the exotic species and the indigenous species? That's what we are trying to do, okay? So we assign a coefficient to the average of A, and we also assign a coefficient to the average of B, assign a coefficient to the average of C and D. Why don't we assign one? Because now, remember, we want to get the difference between the exotic and the difference between the indigenous. We are getting the average of the exotic minus the average of the indigenous. That's why for the exotic, we've assigned positive, and the indigenous we've assigned negative. So that when we get their means, we add the mean of the exotic over 2 minus the mean of the indigenous over 2. That's why we have this line here. So I say that when we run this line, okay, I think I can do Control L to clear my console so that is more clear. So if I run, I get this output here. What R has done is it has taken the average for A and C minus the average for B and D, and this is the estimated difference between the mean of A and C and B and D. Okay, instead of having A minus C as a one comparison, it has taken the average of the A and C and also the average of B and D, then take a difference. Is that difference significant? This is what the contrast has done. Then it has attached a standard error of the difference, the t-value, and the p-value. So we are saying that since the p-value is smaller than 0.05, overall, there are differences between the growth rate of the exotic and the indigenous. And because this estimate is negative, we are taking exotic minus indigenous, meaning that the indigenous are growing faster than the exotic species. That's why we have a negative estimate. So let me see in the chart. Does that clear the problem? Object species not found. Okay. Okay, somebody is saying yes, it does clear. Now, species, I'm also going to explain that. Let me explain about species. We go back a little bit. You remember when you were doing analysis of variance, there were two alternatives. There is an alternative of using LM, where the object was status.ANOVA. So when I came to doing AOV function, using AOV to produce the analysis of variance, I named my model that consists of that information of ANOVA species. So in your line 53, if you run that line, you are going to get the result species. There's no way it's not going to be there if you're running the same script like me. So there's a problem that object species not found. If it's not found, go back and run the AOV command or function. Then you'll be able to get the ANOVA function. And it is what we are testing. We are testing that information there in the object species without S. Okay? So I told you this is just a name. It doesn't have any meaning. Okay. So let me see in the chat. Is that okay? Can we go on? How do we adjust the text of the bar graph? How do we... Okay. Okay, so can we go on? Some of the nitty-gritty, we can do them during our free time. Okay? You can actually add in things. You can make it more beautiful. You can give it an outline. You can go to the Google if you want, like, how can I add this to my graph in R? If you have more than 4 species, e.g. 10, do you still manually code for contrast? Yes. You can see that when it came to writing the contrast, yes. But remember, you're not going to compare all the 10 at once. The pre-planned comparisons are the comparisons that you want to test. You might find that in the 10 different isolates or different genotypes, there are those which are from a female plant, and there are those from male plants. And you want to compare overall. Do are females different from male? So in that case, we are going to write 1 over something, like 1 over 5, 1 over 5 for the 5 versus 1 over 5 for the other 5. That's what we are going to do. Okay? In R, to do the contrast. Okay. Let's go on. The next part is also another way of doing another comparison, which you can do in your free time. Let's go and check assumptions. We can check the assumptions of the analysis of variance model. Either we've used LM or AOV. So here I've chosen to use AOV. I can use the object of LM. So you can, to be able to check for constant variance, you can say plot the object. The object has that model, which is showing us the analysis of variance table. So if we run that, in the console, it's going to say, hit return to see the next plot. So let us all focus on the console. If you read in your console, you will see something saying hit return to see the next plot. So if you hit return, you're going to see a graph drawn in your graphical part. Okay. Okay. So I want to lower this down. Yes. If you look at the plot part of it in the lower bottom corner, we see a plot of residuals versus fitted value, which tests for homogeneity of variance as one of the assumptions under ANOVA. And if there is homogeneity of variance, we just see a random scatter of points. Here we are seeing that the points are grouped according to the different types of categories, but there's no definite pattern. Okay? So I first of all want to go to the next command, then explain more about the residual plots. So if you hit return again in the console, you'll see another plot coming up. But we can have all the plots in one go. So if you go to line 106, you can use the function par to be able to draw all the plots at a go. Now, in this function, we also specify that we want you to combine, we want R to combine our plots in a 2 by 2. The column, the rows are going to be 2 and also the columns 2. That's why you see combine 2, 2. So let's run that. And then we run plot. Okay. What is it saying? Oh. Let me go back. Let me do graphics off so that I clear that. Okay, so I'm going to rerun this part here, line 106, and then plot species. So the first line, so it's saying figure margin is too large, meaning that this part here has been reduced. So I need to zoom in. So I'm going to zoom out to reduce the figure margins. So for me to see those plots, I need to zoom out, reduce the margins. Okay, continue a bit. Of course, these have become so small. Okay, so I'm going to plot again, species. And there they come. So I'm going to zoom these out and then share. Okay, so I hope this is visible to everybody. Okay, we have our first plot here, testing for homogeneity or variance. The variance of the residuals should be constant or homogeneous. And if you look at the first plot, we see that it is a random scat of points. There's no pattern. If these values were either increasing with the fitted values, then the variance would be increasing. If we had a pattern, for example, a bow-shaped curve, then the variance would be increasing. So in this case, we can see that our variance is constant because it's a random scat of points. And the normal probability plot, if you go to QQ plot, that is the normal probability plot. If the values lie on that line that go through, then we also have normal distribution of residues. So I want us to stop sharing. I want to go to share a board and then do some description of how do you know that the variance is not constant. Okay, so let me briefly stop sharing. Let me go and share the whiteboard. Okay, so I am going to draw a plot. Sorry about my drawing. I'm not a mathematician. So this is my plot. We have Y. Those are fitted values. This is residual. Okay. Then we have dots. I hope this can give me dots. Is it visible? Okay. So let me see. Format, let me use black. I think maybe black is better. So we have this. Let me draw them, assuming these are our points we have. Sorry about the drawing, but hopefully to bring out something better. A random scat of points. So if you have a random scat of points, no pattern in it, then that is homogeneity of residuals. Okay, we have a random scatter of points. Okay, now if you have something that deviates from this, so let me erase everything. Okay, then I want to draw another plot. This time I'm drawing a better one. Ooh. Thomas is laughing at me. Can you imagine? Okay, this time I've drawn a better one. This is so if you want to put text, undo. So this is our residuals, and also here, this is our fitted values. Okay, now I'm going to use this to draw our points. If there is no constant variance, we will have them. Those are going to be, this is how it's going to be. They are increasing with increasing fitted values. Okay, you can see I'm trying to make it look real. You can see, so we have a funnel shaped, so maybe there are some values here and also here. So it is a funnel shaped, not a random scatter. It should be a funnel shaped, only that my funnel is not really very funnel, but a funnel shaped showing a V, indicating that the residuals on the y-axis are increasing with increasing fitted values. Then that shows that the variance is not constant. And you can stabilize that variance using various ways. You can use natural log transformation, depending on the type of homogeneity you have or heterogeneity. Okay, so you can use a square. So this is one way. So if you have a funnel shaped, sometimes you can have a bow shaped. So I'm going to erase this. Okay, then I want to draw a line again. So again, fitted values versus okay, so I wanted to draw a curve, but I don't know whether it can. Okay, so if you have something like this, bow shaped, okay, so the values are like that. The residuals is increasing with fitted values, and it has a bow shaped. So remember, these are positives, and I mean these are negatives down here and positive. So that shows that, first of all, the model that you have used is not adequate to model this data. It also shows that the response is binary because some are positive and negative. So you need to run a logistic regression, not ANOVA, the normal ANOVA, where you are assuming that the response is normally distributed. So that's what it means, okay, when it comes to constant variance. So you can either see a funnel shaped increasing variance, which can be stabilized by either using natural logarithm, or you can square the response or you can use depending on the type of shape of the graph. So here we have the bow shaped. It should be a very nice bow, not like mine, crooked. But it is telling us that our response has positive and negative, meaning it has two outcomes. Yes or no, germinated, did not germinate. So just running ANOVA is not suitable for this data. And we need to run a logistic regression, which is going to model the distribution of the data. And in this case, the distribution will follow a binomial. That's why we are choosing a logistic regression. Okay, so I hope this is clear. I'm going to erase this. Any question? Okay, so then we say that if we want to know normality, we should have a bell-shaped, or the values in a normal probability plot, the QQ plot, should fall on the blue line as we saw. Then that shows normality. Any deviation from that shows that the data is not normally distributed. So we can also use natural logarithm to convert our data to normality. Then independence. So let me draw independence. Normally independence occurs if you have time in your data. So like you've measured the data on the same experimental unit over time. So now, assuming your curve is like this one. So I'm going to try and draw something. So I am assuming that I'm really okay. So I hope this brings out some picture. So remember, if there is no pattern, then we have independence of residues. But if you get a pattern where we have troughs and peaks, that means that there is a time component in your data, and you need to model your data over time. Then in that case, we need to use repeated measurements to take into account the time component. You've measured your response on the same experimental unit over time, and you ignored the time component. But when you go to run the residual plots, you find that you have this type of residual plots where you have troughs and peaks, where you have a time series graph. So in that case, we now run our repeated measurements using either the different types, as we shall see, to account for the time factor in your data. So those are the ways we can test for our assumptions. Now, the last thing we are going to look at, I'm going to close this out. And then share our R. And then ask in the chat. Because I'm going now to change to, in the case of non-homogeneous variance, which kind of logistic regression? I said in order to conduct a logistic regression, your response should have two outcomes, yes and no. And you can view that in the residual plots of residuals versus fitted values, where you get a bow-shaped curve. That's when you can run a logistic regression. And if you have increasing variance, the residuals are increasing and the fitted values are also increasing, that means that the variance is not constant. And then we can use natural logarithm to stabilize the variance. Problem is fitting all of them. How do you reduce size? Which size? That question is not very clear, Elton. Make the question more clear. Okay, if I can ask in the chat, can I move on to factorial? Because we are running out of time. We want to see what happens in R when we have data coming from factorial. How do you fit all of them in one graph? Oh, the graphs. Okay, I'm going to do that in 1 minute and you see that. Okay, thank you. How do you draw the graphs? To fit them in one graph, all of them. So if you go to line 106, that is the command. The function is PAR in bracket M F row. It's telling us that you're specifying that the rows should be 2 rows and then we have 2 columns. Okay, so that's how you're going to run. You can actually change instead of rows and put column. It's also going to draw them in a different way. So if you run that command on line 106 and then you plot, so you see the plot command. So you've specified that my window should be a 2 by 2, meaning you're going to have 2 graphs on each row. Then you run the plot part and we are going to see the figures in our plot window. Okay, now I have here an error saying the hat values for the last plot, which would have been the plot of independence. It is telling us that most of the values are similar, so they can't really draw the plot. Okay, so for us to erase the graphs, we can use graphics off. So just run that. And to remove the command of having the 2 rows on each row, let's have 2. You can remove by specifying the same command and put in 1 1 so that you only receive 1 graph per row. Okay, so let's go on. So here we have a 2-way ANOVA. Remember, the data is called yield. So we read in our data. This time I think we should move a bit faster because we know how to import data. Just run those commands. If you use the head command, you will see the first 6 rows. If you use str, it tells us that in your dataset yield, the block is interval, the date is character, variate is interval, and yield is numeric. So this is a 2-way ANOVA, and that is the dataset is called yield. We would like to convert block to a factor and variety to a factor. So you already know that. Let's just run line 121 and line 122. And then if we run again, the structure of the data, we'll see that block and variety have been converted into factor. Remember that when I was converting them into factors, I used a small, my name of the object is yield $block with a small b. Yet in the original data set, the original block is capital B. So don't get confused about that. So when you're writing you remember the way you've written, or we can actually change them and rerun so that we don't confuse ourselves. So I've changed yield capital B, yield capital V, and when you just run those two and run, we see that our blocks are. Then you come to fit ANOVA for a CRBD, and it is fit. Fit is the object, assign AOV, an isovariance, yield is a function of block plus variety, and data is called yield. So let's run that and also run. So if we look at our 2-way ANOVA, it has a block effect and a variety effect. We are interested in the effect of the variety on the yield. So we look at the p-value for variety, and we see that it is not significant. And since it's not significant, we cannot run anymore the treatment pairwise comparisons. That's where we end. So we say the effect of variety is non-significant, meaning that whichever variety you grow, you won't get any significant yield from the other. Okay? Then the rest of the commands I've put is for you to learn, to use for learning, but we are not going to run them because our analysis of variance is non-significant. Okay, lastly but not least, let's run the factorial. And the data set is called factorial.csv. We are going to read that data set in using the command on 143. And we had our data consists of nitrogen levels and consists of 2 crops and then yield. I want to go in the chart. Am I being very fast? You didn't load the associated package. Okay, my variety, okay. Am I being very fast? Says the pace is fine. Others are saying yes. So I don't know. Yes, I'm not very fast. Yes, I'm fast. Pace is fine. Okay. Okay, good. Okay. Okay. Okay, what I'm going to do, I'm going to rerun line 143. It's just reading the data in. And then I use the head function to see the first 6 rows of our data set. And we have 3 variables: nitrogen levels, crop, different types of crop, and yield. And you can look at the environment and look at how many observations you have. STR for the structure of the data set. And it says that if you look in the console, nitrogen is an interval, crop is a character, and yield is numeric. We want to convert nitrogen and crop to a factor. Then you can also use column names to see what columns you have, the names of the columns, so that when you're writing your commands, you don't write the wrong names. Okay, so now we are changing nitrogen using as dot factor, line 145, and checking whether it is okay. It has been converted to a factor. Then crop, check whether crop. So all of them now are converted to factor. And then we are going to use mod 3 is the object. AOV is, we want to get an analysis of variance for yield, and yield is a function of nitrogen times crop because we want to get the interaction, and the data is called fact. Okay, so we run line 149 and then run the summary, and it gives us the output. I didn't send it. Oh, I'm told I didn't send the data set. Oh my dear, I'm very, very sorry. I am very sorry. Can I paste it in the chat? Maybe I try putting it in the chat now. Let me do that. So that, let me paste the data in the chat. I didn't know that. Okay. So I'm pasting the, please don't write anymore. Okay, let me paste the data again. I'm going to paste the data again. That was, there it is. So please pick it. In Q&A, Dr. Helen will paste it there. So let me paste it again. Please don't write any comment in the Q&A, otherwise you're going to make me post this thing 100 times. Factorial, I'm pasting. Okay. Okay. Okay, there we are, and I'm giving you 2 minutes to download that data set. Okay, share to everyone. Oh, okay. Let me share to everyone. Thank you about that. I was sharing to the panelists only. That is, okay, there we go. Let me share it again. Factorial. Okay, there we go. Okay, have you got now you can write, did you get the data set? Were you able to download it? It's called Factorial SV. Oh, Sarah is saying no. Seriously? Let me paste it again. Okay, now can you stop the comments so that I can send it again? Factorial, open. Okay, there we go. Not on phone. Beatrice. Beatrice, you should have got a laptop. However, it is in Day5 material. You've put it there. If you go to the Google link, it has been inserted in Day5 material. So Dr. Helen will post the Google link to Q&A, and also all others will get it. I am sorry about that. The weekend must have turned my head upside down. Thomas is making fun of me, but it is okay. Since you can't see me, you won't know the fun. Okay. I hope now you've got it. You've got the data. And let's go back and run. Okay. Oh dear, don't worry about that. You just pick the data set. Dennis is saying pre-Valentine weekend. Probably, I'm not very sure. I don't celebrate Valentine. Okay, so can we now go on to the factorial command? Can I see in the chat? Should we go on so that I don't leave anybody behind? Okay, thank you very much. Thank you. Somebody wants Day5 attendance list. Okay, good to go. Thank you. Let's go to the R. Okay, so we are going to read, just now run the command, and the object is called fact assign read.sv in bracket factorial. So remember that you put it in the directorate where you set R2. If you put it in a different directorate, folder, it is not going to run. It's going to give you mistakes. So let's put it in that particular folder where you set R to be looking for all those data sets you're talking about. Okay. So you run the first command. Okay. And then click head to see whether you see anything. Let me see in the chat. Is everybody able to import the data set? Are you able to import the data set? Okay, great. Thank you. Okay, let's run. Okay, if you're able to import the data set, can you view the data set? Click head in bracket fact, then click str in bracket to see the structure of the data set. So you will see that nitrogen is an interval, crop is a character, and yield is numeric. But we want nitrogen and crop to be factors. So the next command, which is line 144, is just showing how the names are written in the data set. You can just run it. And let's now convert nitrogen and crop to factor. So I'm using as dot factor. So run line 145 and check the structure. It has converted nitrogen, and then run line 147 and then structure. So now we are good to go. Let me see in the chat. Is everybody able to convert? Thank you, Dennis. Where do I find you with the matoke and kuku? Okay. So if you're able to, somebody has an error. Let me see. Giving error. If it's giving error, then you can make sure you have fact $ nitrogen written well, and you can use the fact command. So instead of that, if you can write nitrogen assign factor in bracket fact $ nitrogen. Okay, so you can either use the fact as factor or fact, one of the two. So you can see that in the R Studio, I've written nitrogen assign fact factor $ nitrogen. So you can use either of the two if you have an error. Okay, so let's go to the last part of our practicals. That is the running the model. I've called it model 3. Then I'm assigning AOV. Yield is a function of nitrogen times crop to specify the interaction. Then data equals fact. So let's run that and run the summary. Okay, so let's look at the console. Let's look at the console and interpret our results. So I'm going to zoom in to make them a bit larger. Zoom in. Zoom in. Okay, there we go. So our results, if you look down here in the console where there is model summary mode 3, nitrogen crop, the first thing we do is look at the interaction. That's nitrogen semicolon crop, that's the interaction. So if you look at the probability for the interaction, the value 3.4 times 10 to the power minus 7, it is smaller than 0.05, indicating that there is a significant interaction between nitrogen and crop, meaning that the yield of the crops vary with different levels of nitrogen. So if you have crop alpha, you will get different yield when you are at 0 nitrogen, 50 nitrogen, and 100 nitrogen level. If you have groundnuts and you apply nitrogen, you'll get different yield at 0, 50, and 100. That's what the interaction means, that the yield depends on a combination of nitrogen and the type of crop for it to change. Okay? Okay, so once you get a significant interaction, we construct as an interaction plot. So let's construct an interaction plot. So here where there is interaction plot, there are many. You can use one of them. I'm going to use one of them because of time. So we have our interaction plot. I'm going to zoom in and share the interaction plot. That is what we've gotten, our interaction plot. And if we look at down here, we have nitrogen levels 0, 50, and 100, and the mean yield on the y-axis. Now, if we look at alfalfa, it's the one with dotted and big spaces. Or let's look at the one with the highest yield. That is soybean. If you look at soybean, that is with the solid line. At 0, at no nitrogen, it has the highest yield. As you put in nitrogen, increase the nitrogen, the yield is decreasing. Why? Because soybean is already nitrogen fixing. So when you put in nitrogen, actually you're poisoning it. So that's why you see the yield decreasing. Then if we look at groundnuts has dotted, the dotted lines. At 0 nitrogen, we have higher yield. If you put in 50, the yield goes on decreasing. Because also, I think also groundnut is nitrogen fixing. If we look at alfalfa is where my cursor is. It has a higher yield at 0 nitrogen, but as you put in more nitrogen, the yield is decreasing. So what do we recommend to the farmers? That when you're growing these 3 crops, we shouldn't actually apply nitrogen, unless if the soil is showing that it is deficient, okay? So I was telling you that when the interaction is significant, you don't need again to look at the crop effect and also the nitrogen effect, because now we can see that we can look at the crop effect. We can know that soybean performs better than all the crops. And the nitrogen effect, we can see that if you're increasing nitrogen levels, the yield is lowering. So we don't need actually to apply any nitrogen for that particular soil. Now, if you move from 0 to 50 for soybean, the yield is changing. That is what we call the interaction. From 0 to 50 for soybean, the yield is decreasing and continues decreasing. If we look at another crop, the same pattern, decreasing. So if there was no interaction, these lines would be parallel, meaning that if you change from 0 to 50, there is no change in yield. The yield is just the same, okay? There would be parallel lines with no interaction. Okay, I think I'm going to stop sharing. Can we give lines different colors? Yes, we can do that. Different crops? Yes, we can do that. And that is going to be your assignment. Okay? We are going to analyze our data of interaction tomorrow and assign it different colors. You've really given me an idea of the So let's try to draw our plot. Is that the data which I have used actual or hypothetical? It's actual data, only that some of the values have been removed. It's not the whole data set, okay? So tomorrow, I would like you to draw the interaction plots with different colors as our assignment. So we will have people presenting, at least 2 people presenting in the morning. Then in addition to what my colleague Thomas is going to do. So probably he also has something else to give you. But if I find a data set that I can post in the folder before the end of the day, I'll also give you another assignment. But for now, my assignment is draw the interaction plots with different colors so that they are visible. Tomorrow we'll see them. So for now, you need a break, I'm told. And we have 11 minutes to 1. So we will take all those minutes off, isn't it? Agreed among the facilitators that you take off the 11 minutes, you come back at 1, and Thomas will be with you. Thank you very much for being excellent participants. Enjoy the break. And make sure you do the assignment. The assignment is construct interaction plots, assigning different colors. So we've already done that in the exploratory data analysis. Go there, pick that command, and put it in this script, and tomorrow we see you. So thank you so much. Enjoy the break. Let me see you at 1. I hand over to Dr. Thomas. He's saying that he was enjoying and doing the work. I'm getting the hang of it. Wow. Onyango, I don't celebrate Valentine because every day is my love day. So I do not celebrate Valentine. Thank you very much. Your microphone is clear today. Thank you, Jordan. You joined late. Document. Helen posted the Google link. Somebody needs the documents. Okay. Okay. Thank you. I am also going for a break. Attendance, please. And in addition to the Google link, yes, Helen has already posted the attendance and the Google link to both the Q&A and the chat. Thank you very much. You've been excellent participants. Richard, the documents have been shared already. Check the Google link and both in Q&A and the chat. Okay, George, thank you so much. Jackson, thank you so much. See you, please go for the break so that I can also go for the break. Okay, bye-bye.
Hello. Hello. Are we back? Are you getting me? Oh. Hello? Are you getting me? Okay, thank you very much. I'm going to pick up from where my friend Susan has left, and then we'll see how far we can go. I would like to wish everybody a happy Valentine. I think there's no better gift for Valentine than a full dose of statistics with R. So this is the best gift from us to you for this very lovely day. I saw a few questions in the chat and Q&A relating to split plot, factorial. One of the questions was the different factorial and split plot. Or so I want to make a few things clear. First is that when we are talking about experimental design, we should be able to differentiate two different aspects. So the first thing is we need to talk about the treatment that we're handling. So the treatment are the things that we are testing. Now, when we talk about the treatment, the terms that comes up frequently are what called factors, especially the last part of the presentation of Susan talks about factorial. So with factorial, that means you have two or more factors being tested at the same time. And I remember the other day we defined a factor as a group of treatment that are similar. So variety, if you have 5 varieties that you're testing, the 5 varieties can be categorized under one factor, which is a variety. Then if you have 3 levels of nitrogen fertilizer, then that can also be categorized as nitrogen as a factor. Now, and then when you have the two combinations, so you have 5 by say 3, that means you have 15 different combinations of treatment. Now that what I've talked about now is what we call a treatment structure. So relating what are we testing, how many treatments are there, how many factors are there, and that. Now when it comes to the design itself, so in the technical term, the design is related to how the experimental material is manipulated when it comes to setting up an experiment. So for example, sorry, I was not, so for example, if you're using, say you're using animals as your experimental material. So you want to say, okay, how many animals do I have? Do they look different? Are they similar in terms of weight, in terms of, are they the same breed? That kind of thing. So that is what we're relating to our experimental design. So the combination of the treatment and the experimental material will now constitute what we have the design. So a split plot is one of the design that is used, but a split plot is only used when you have a factorial experiment. If it is not factorial, you cannot use a split plot. Is a factorial experiment or factorial treatment structure can also be handled with any of the other design, whether completely randomized design, randomized complete block design, Latin square, incomplete block design, and so on and so forth. Okay, so that's what I want to, the clarification I would like to make. Now I want to start on with the split plot, analysis of split plot. So the first thing is we are going to start with an example from the package mass. So we need to install the package mass. So this is a split plot design in RCBD. So we're saying, so RCBD, let me pick my pen first. So I want to have this. So we say split plot can be with any of the design that we talk about, the standard design. So here we have 6 different blocks, and then remember with split plot we should be having a factorial experiment. So we have 2 factors here. We have the factor that we're going to put on the main plot, and then we have the factor that we're going to put on the subplot. So the variety in this case is going to be what we put on the bigger plot, the whole plot or the main plot. And there are 3 varieties here. There is variety called Golden Rain, there's variety called Marvelous, and then there's variety called Victory. And then the second factor is nitrogen fertilizer. So the nitrogen here is going to be at 4 levels. There is 0, that is the control where you don't apply anything. And then you have 0.2, 0.4, and 0.6. So as you can see here, our nitrogen is a quantitative factor. So a quantitative factor, that means you're increasing the amount as you move from one level to the other. And with this quantitative factor, your interest may be actually to determine whether there is actually what kind of response are we looking at? Are we looking at a linear response? Are we looking at a quadratic response? Or are we looking at, say, a curvilinear response? So these are the things that you can always handle after you've done the analysis of variance. You have the script with you, but this is just going to be the script that we are going to run. I will just talk briefly about the script. So the first thing is that we need to define our treatment. So we have factor 1, which has 3 levels. We have golden rain, we have marvelous, and then we have victory. Now, we already know why we put this thing in brackets. So we are creating a vector with 3 elements. The second one here, we're going to create another vector, this time with 4 different elements. So these are our main plot, and this is our subplot. So remember, we already looked at the design.split plot. And design.split plot is from the package Agricole. Now, a number of you were trying to run a program and you say, oh, lsd.test is not found. snk.test is not found. That means the mother package that is supposed to contain those functions, you did not install, either you did not install them or you did not call them when you actually running. So make sure that the packages are installed, and make sure when you're starting to run, then you call you use the term library to call the packages. You only install once, but using the function library to call a function or call a package, you need to do it every time you open R to run. Okay, so this is what we define. We define this, which is this one here, and then the next one here is that one there. And then you're telling the program that you have 6 replication, and you're telling program that the design that we are going to use with the split plot is going to be randomized complete block design. And then the other day we talked about what a series is. So this one will give us 1, 1, 1, 2, and so on. Our plot will be leveled. Okay. So with this command here, you're going to run, and then you're going to generate an output. So this is our output, which is also an object. And remember, this object here has lists, several lists in them. So one of the things that we are interested in what is called a book. That's the field book that, you know, I mean, those who are doing agriculture experimentation, you know that when you're going to the field, you have a field map. So this kind of a field map that will give you. Of course, this is how the output will look like. So this is our plot. This is what is got from series 1. You have 1, 1, 1, 1, 1, 1. So you can see from here that this is our main plot 1. And this main plot here is divided into 4 different subplots. Okay. And these are part there in block number 1. So you can see here now that here, because we are talking here about one main plot, which has golden rain. Okay. I have a nice picture that I'm going to show you today, how the whole thing. Now, this is important because when you're going to run analysis of variance, remember, Susan talked about the 2-way analysis of variance where you have 2 different factors. Now, in this case, we have to be a little bit careful, especially when we're looking at the main plot factor and then the subplot factor. So this is how our analysis will go on. Let me just first clean this up a little bit. Okay. Okay. So what we have here is then that we have our plot 1. Okay, let me just show it. Okay, so this is the whole thing here. So the first thing that we do, we have two factors. So we have variety, which is going to be on a bigger plot. So look here. So here we have our block number 1, block number 2, block number 3, number 4, number 5, and number 6. Now, when we did the randomization, so the first thing that we do is let's look at block number 1. This is our block number 1. Okay. Now, after you prepared your field very well, this is our block number 1. There's also a nice red color here for Valentine down here. Okay, so what we're going to do now, because remember we have 3 different varieties. From here, we have 3 different varieties. We have golden red, we have marvelous, we have victory. Now, these are the ones that are supposed to be assigned on the main plot. So here, the first main plot will have golden rain. The second one will have marvelous. The third one will have victory. Now that is, remember, this is randomized complete block design. So you do your randomization block by block. Once we are done with this, we move, we do the next one, we move, we do the third one, the fourth one, the fifth one, and the sixth one. So this is, we are only looking at one factor, we're looking at variety. Now with the split plot, what will happen is that we say, okay, if we look at this particular plot here, this one here that contain our golden red, we need to split it up so that we also apply the 4 levels of fertilizer there. So when we come here, then we have the same plot here. Okay, so we broke it up into 4 different parts. We are splitting it, that's why we call it a split plot. And then, so the G is constant because the G is coming from here. The whole of this is the G, okay? And then we are breaking this into 4. Then we have 0.6 falling into the first subplot, 0.2 falling in the second subplot, 0.4 falling in the third subplot, and then 0.0 falls into the fourth subplot. Now, I put in a caution here that beware of a pseudo replication. Now, what we have here is that as far as we are concerned with G in this block here has only 1 block. Okay, there's only 1 here, but then the temptation would be to count this 1, 2, 3, 4 as our replicate for G. Why is it wrong to count this as replicate for G? Can I have some answers in the chat? Can I have some answers in this chat, please? Pseudo replication. Okay. Okay, it's an independent application of treatment. Okay. Okay, good. I think we are together at this point. Okay. So now the thing here is that if you go into analysis of variance and you run the analysis of variance like Madam Susan was showing you, you're going to have a problem with the split plot because you're going to assume that the pseudo replicate will actually appear like actual replicate when it comes to the genotype. But when we come to the fertilizer, we don't have any problem. So this is before splitting and this is after splitting. Okay, so now, of course, at the end of the day, we need to start our analysis by doing summary statistics. I think this one here, my good friend did it very ably. So here, the first thing that we're going to do, if you're going to draw a ggplot, the first thing is you need to install the library ggplot2. And note here that the function here is ggplot, but the package is ggplot2. So don't confuse them. So you need to install it and then you need to call it. Okay. So here I put my small note in my R. I tell you that. And now I did something a little bit different from what you've seen so far. So what I did here is I created an object called plot0. Okay. And plot0, I use this function here to assign. So I want on my x-axis, I want to have nitrogen, On my y-axis, I want to have yield. And then the data that I'm going to use here is the data called odds. Okay. So I created this. This is the first layer of my ggplot. They say ggplot is built layer by layer. In the second layer now, I bring it. So what I do is I get my same object here. I add something. So what I'm doing, I'm actually now building onto the same base that I've created. So I'm creating another object, the same called plot 0. Now I picked my previous plot 0, and then I add a geobox plot to it. So it creates a new, now it's an update. So like I build the second layer. Then I take the third layer. I build a third layer by bringing this. So what I want is by the facet here, I will now make for each block, I will make a different box plot. And then for the theme here, I'm saying the background, what do I want to have in the background? And then finally, I'm going to use this plot O to actually now print for me the graphs that I have. So at each stage that you run this, you're not going to see anything on your screen. The last thing that you will see up on the screen after you run this particular function here. So let's look here. So this is our block number 1. So from block number 1, we see that, well, as we increase the amount of nitrogen fertilizer, the yield seems to be increasing. So we're looking at some kind of a linear relationship between the amount of fertilizer and yield. Now, if you go to block 2, we seems to be having something similar to that. If you go to block 3, well, we seems to be having something like that, but then it seems to level off at some point, okay? And then if you go here, you have something like that, you have something like that, you have something like that. So from here, one can say, well, it looks like the more fertilizer we add, the more yield will increase. And this seems to be consistent from block to block, except block number 3 seems to behave in a different way. You can also see from here, you can actually see from here that the worst, of course, the control, like what we have, let me clean it up a little bit. Okay. So here, what we see is that the control is actually the lowest in all the blocks, okay? And then the highest level of 0.6 seems to be the highest in all the blocks, okay? That's one thing that we can see. You can look at the middle to actually see. I think Susan already talked about this. So the next thing that we can see here is, okay, what other information do we have from here? We can also look at the variability within the different, so for you see now when we look at the control, all the plots that were having the control seems to have their yield around 75. And they're very close together. So that means there's very little variability in this. So there's very low variability here compared to at 0.4. 0.4 seems to be having values spread over a wider area. Okay. And when you come to plot number 4, we seem to have very low variability. So low variability in a plot could also mean that either the plot is so bad that everybody is restricted in their response or whatever it is. And we are going to see also when you're looking at multi-environment trials, like for different genotype, you can also just look at the box plot to can tell whether there's actually genotype by environment interaction. So this is a brief, this is already part of the exploratory data analysis. You see, once I look at my things like this, I will not be surprised if I see that the nitrogen has a significant effect, because from my exploratory data analysis, I already can see there's some kind of a trend going on. I can do the same for the variety. So you can see, if you look here in plot number 1, that the variety seems to be not to be the difference between the different varieties seems not to really matter that much. Now I want to ask a question. Which is the I mean, this is crop yield. So which one is the most fertile plot in this case? Can I see some answers in the chat? Which is the most which is the most fertile plot according to you? Block, rather. I see block 1, 1, 1, 1, 1, 1. Okay, why? Why? Higher yield, of course, that's what we see from there. And the reason why we block is because we think blocks have different, the blocks affects the response variable, which is yield. So we can see from here that this one actually has a high yield. And then the worst one probably is block number 5 and block number 6. So it looks like we could be having, this is the most fertile area. We are going down. So by the time we reach here, we're going to the least fertile area. And that is, remember when we talk about randomized complete block design. So this is what we can pick. So from here, I can probably see that the variety seems not to be different. As I can see, the mean seems to be closer together, but the fertilizer seems to have some differences. Now, since we have two factors, we have variety and fertilizer, what we could do, we could combine the two together and actually see whether there is anything like the interaction between the two. So this one brings us to this lovely plot that Ara can give you. I know each one of you can now generate this plot. So at the end of the day, if you have ggplot2, you have your data into a folder, a nice folder. What you simply need to do is change my nitrogen into your variable, change my yield, and then you can run, and you can actually generate something like this. So what you can see from here is also, we seem to see the same pattern, that there's increase, there's increase, there's increase, there's increase, there's some kind of ink, but there seems to be kind of a leveling off somewhere here like that. And this is also going to help you actually to select models. And remember the assumptions of analysis of variance are things like variability have to be constant in the different group. So from here, I can tell whether variability is constant or not. From here, I can actually tell whether I have differences, variation in heterogeneity or homogeneity, as we talked about. So before you go to do your data analysis, you already actually know what is going on in your data, and you will not get in shock of your life because you know where the story is going next. Okay, so we are going to run these programs later, and we'll have no problem running it. So from here we can see that the pattern seems to be the same. Let me first grab up my, you see the pattern here seems to be the same, although we seem to see the different variety seems to change. You see, if you look here, Marvelous is in this block seems to be the best. Okay, while here Marvelous it performs very poorly at a higher nitrogen compared to, say, the Victory. Victory seems to be. So here you could also be thinking, well, there seems to be some interaction here in that the variety seems to change their, they seems to change something. But one thing we don't want is, we don't want to have an interaction between the block and the treatment, because that makes the assumptions of analysis of variance to be violated. One of the assumptions of analysis of variance is that the treatment effect and the block effect are supposed to be additive. Okay. So what I want to show here is that we can run the ordinary analysis of variance like the way Susan was doing. So we want to say, can ordinary analysis of variance and/or split plot design? The answer is no. Why the answer is no is the issue of pseudo replication. It is going to give you a false. It will tell you that you've replicated variety more times than the actual number of replication. And once the higher the replications, replication increases the power to detect differences. So you're going to get a false sense of differences between varieties simply because you've used false number of number of replications. So this is a simple command that we can run. And somebody asked, why do we run AOV and then we also run LM and then we also run what? Well, they give us similar results. I mean, sometimes it's just different flavors that people put in. You need to be able to, when you're going to interpret the result, then you may have to change a little bit. There's just some little flavor here and there, but we're going to explain. So what we do is, I have these scripts with you. We are going to run it after I've talked. So this, we create an object called fit.aov, which is the analysis of variance. And then later, we look at summary. Okay, so the summary will give us some results. Okay, so here, this is what will happen. Now this is from a classical biometric class. They teach you that the number of degrees of freedom for a block will be the total number of block minus 1. So in this case, we have 6 blocks. So this would be, so we don't have, this is correct, degrees of freedom. The next one, we have 3 varieties. So 3 minus 1, 2, this is also correct. We have 4 nitrogen levels. So 4 minus 1 is 3, that is correct. And then the interaction between nitrogen and that, yeah, is the product. That's well, we said for now, that's also okay. Now the problem is going to come here. Okay, so remember here, when we are calculating, let's say we are calculating this, we're calculating this value here. Now this value here, which is our F, is calculated as mean. So we have here mean sums of squares for variety, divide by mean sums of squares for residual. Okay, so this is what we call our numerator. I was taught this one here when I was in primary 4, I think, when most of you were not yet born. And then here is, this is our denominator. So what when we are going to look into an F table, you need to know the value of the degrees of freedom of the numerator and the degrees of freedom of the denominator. So here then you're going to look at this value here. You're going to have there are 2 degrees of freedom for the upper one, which is the variety, and then there are 2 degrees of freedom for the residual. There are 55 degrees of freedom for the residual. Now, the 55 degrees of freedom for residual would count this as 1, 2, 3, 4 replication, and yet we know this is only 1. So this is where this value here that you get here is going to be wrong, and whatever result that we get here is actually these 2 results here are wrong. Okay, because the block and the variety are only dealing with with level 1. So this is what we are doing, what we are dealing with. So we only have 1, 2, 3, 4, 5, 6 number of blocks. So we need, actually, what would happen with that, with a split plot analysis, you actually need to do 2 different levels of analysis. You analyze the main plot differently, and then you analyze the subplot differently. So this analysis here is wrong for a split plot because it is it gives a lot of power to what we have as the main plot factor, which is the variety in this case. So this analysis is wrong. The correct degrees of freedom actually is supposed to be 10. The correct degrees of freedom for testing this and testing that is supposed to be 10. So we need to look at an analysis that will give us the degrees of freedom of 10 instead of the 55. Okay, so this is then we come and analyze using a different function here. So this is LMER function. So we plot now a different one. as you can see, what remains inside here is like, this is yield, this is our response variable. We have our block here. We have our variety. So what this one means is that variety times nitrogen. So what this one means is I want the effect of the variety plus the effect of block of nitrogen plus the interaction between them. One of the most strange thing with R, how it writes the interaction term is a bit funny to me, but just because I started my work with GenStat, so I'm more used to that. So what this one means is we have the main effect for variety, the main effect for nitrogen, then you have the interaction term. Now, the change that we observe is here. So this one defines this, like you have one here, and then you have the interaction between the block and the variety. So what it's telling us is that for the block and the variety, I'm just saying this in a layman way. Say for a block and variety, we are going to use this one here, the interaction between a block and variety, as our error for the analysis. So what this one will tell you here, let me change my pen. Okay, I'm going to get a green pen. Okay, so here, you see now the difference here, the result here, first of all, comes in different form now. Okay, so here it gives you the numerator degrees of freedom and then the denominator degrees of freedom. Remember, I talked about this. I talk about mean sums of squares for variety over mean sums of squares for residual. So this is our numerator, and it has for the block it has degrees of freedom of five. But for our variety here, let's look at this line here. Okay, so here you can see that we have 2 degrees of freedom for our numerator, and then 10 degrees of freedom for our denominator. So this one is for the upper part, and that one is for the lower part. Now, in the previous analysis of variance, all the degrees of freedoms are put in the same column, but here there are 2 columns for the degrees of freedom. There's one for the numerator, which is up, and then the one for the denominator, which is down. So in this case, what we do, let me clean it up a little bit. Okay. Okay. So if we look at the analysis result, let's look at this particular. Okay. So this one tells us that our variety are not significantly different. Okay. Our block is significantly different. The interaction is not significantly different. Of course, we'll not be surprised by the block being significantly different because we saw that the blocks were behaving differently. But we're a bit surprised. We are not surprised that varieties were not significant, because if we look back at you see the varieties, the means are very close together. So we are not surprised, but somehow we're also not surprised that these ones are significant. That's what we saw there. Okay. If we had done the wrong analysis, it would tell us that variety is significant. So you can see now that we would have actually gone ahead to publish our report that we have a significant variety, and yet the actual analysis actually tells you the varieties are not significant. Why the difference in this is the issue of pseudo replication. So the pseudo replication will give us a lot of degrees of freedom, and then with that false confidence, we can go ahead and declare that our results are significant, that there are significant differences between the varieties. So that is one way that you can actually use to analyze this. And what is actually happening this one here, the assumption here is that the block effect, the block and the interaction between the block and the variety is actually random. So we are going to look at the mixed model where we're going to talk about random and we're going to talk about fixed effect. I'm going to explain that when it comes to issue mixed model. But this is the correct analysis, and you can see that there is a difference between the wrong analysis and the correct analysis. So this one, I brought them together now to do the comparison. So this is the actual analysis. The correct analysis will tell you that there is a significance. There's no significant difference between the varieties, while the wrong analysis will tell us that there is a significant difference between the different varieties. So you can see that if you choose the wrong way, you design your study in one way, you analyze it in the wrong way, you likely come up with the wrong conclusion. So for the block effect, the block and variety effect, this is actually what we are analyzing. But for the nitrogen and the interaction between the nitrogen, we analyze the smaller, the subset. These are the ones that we analyze. If you've ever used GenStat before, GenStat actually produces something that's slightly different. So it gives you we have two error terms. We have error term A that is used to analyze the block effect and the variety effect. Then we have error term 2 that is used to analyze the nitrogen effect and the interaction between the nitrogen effect. So this upper part here analyzes for us this one here, okay? So the number of degrees of freedoms are fewer because each block is just divided into 3. So in total here we have 3 times 6, which is 18 degrees of freedom in total. And then this part here will use another degrees of freedom, and this will give us that. So this analysis here gives us the same result as this one here, but this one here is presented into a different form. It has actually been really, really difficult to most of the people who are trained much earlier on in agriculture. This is what they know, and they don't like this one here. It kind of invades their, you know, we all don't want to go into unknowns, but these days the mixed model is actually an area where we all seems to be going. So this is where we need to move our attention to. So I put in the three side by side. So here is the traditional analysis of variance for split plot. That's design. If you ever use GenStat, this is the kind of result that you get, which is the correct one. I give it a long tick. This is the wrong one. Okay. Now, this is the correct one, but this is the most modern one. Now, since most of you are young, I would expect that you adopt these other ones here, so that we don't want to continue promoting ANOVAs while the tractors are there. So, and of course, the ANOVA can dig for you, but the tractor can do for you a much better job. So this is the so that's the first part of the presentation that I actually have here. So maybe I would beg to go to the incomplete block design, and then we can do the experiment, the practical tomorrow in the morning. Okay, is that okay with everybody? I'm going to go to the chat at some point, then we'll answer a few questions. Okay. Okay, so we talked about incomplete block design as the design in which, because the size of the blocks are smaller, therefore you cannot take all your treatment, include all your treatment in a block. In a way, if I have 10 treatments, but I only have blocks of size 5, that means half of my treatment will not appear in the block. So the challenge then would be, how do I compare treatment that are not occurring together in the same block in the case of partially incomplete block design? So when you're analyzing incomplete block design, there are 3 types of analysis that you find in literature. So the first one is what we call intra-block analysis. So the intra-block analysis is analysis that we are comfortable with. Then there is what we call so intra mean within the block. So you only make comparison within the block. Inter means you make comparison between the different blocks. So you have intra-block analysis. Then we have the third part, which is recovery of inter-block analysis. So here we want to get both the intra information that we get from intra, we add with the information that we get from inter to actually get a better result. And these are also what we call, these are actually modern, these are modern trends in data analysis. The reason why these ones are picking up, that we are going this direction, is the issue of the mixed model that I'm going to talk about at some point, maybe either on Wednesday or. So the mixed model has really changed things, the way analysis are done. And I would advise all of you to actually go and get yourself acquainted with the mixed model. So we're going to look at the intra-block analysis, the inter-block analysis, and then we're going to look partly at recovery of inter-block information. And then I will also show you the results that I've done. Then tomorrow we are going to do it ourselves. What I would ask you to do it overnight, so that by the time in the morning, we can just ask a few questions and sort it out. Okay, so the intra-block analysis is what we call within the block analysis. So here, what we do is that the treatment effects are estimated after eliminating the block effect. So what we're going to do is we're going to first remove the effect of the block. So assuming now that there are blocks that are more fertile compared to others. So can we first of all remove the effect of the block? Now, once we remove the effect of the block from our data, we remain with some residue. Now that remainder level over is the one now that we are going subject to analysis of variance. So that's what we call intra-block analysis. Now, if the blocking factor is effective, then intra-block analysis is enough to provide reliable, correct, and valid statistical inference. But if the blocking factor is not very effective, sometimes you can block and then different blocks behaves in a different way. One block may be effective, other blocks may not be effective. There may be interaction between treatments and blocks. So in that case, oh, sorry. I was told that I'm too fast. I guess I'm rushing for Valentine, but I will slow down a little bit. Okay. So with the intra-block analysis, what we are going to do here is we are going to first remove the effect of the block. So when you're fitting your model, you need to fit into a model where you say, well, I first need to take away the effect of the block. Okay, then the next thing, then I said, okay, now let me look at my treatment, given that the block is already taken away, and then I'll get my residual. So that's the kind of analysis that we are going to look at. And this is what we call intra-block analysis. In terms of the mixed model, as we are going to talk about, so in this case, we will consider the block effect to be fixed. I'm going to explain what fixed and what random effect is when we are looking at the mixed model. So for now, in this case, we assume that the block effects is fixed, and then we do the analysis, and then we get our interpretation. So this analysis, sometimes it is enough, sometimes it may not be enough, depending on your situation. Then the second analysis is what we call interblock analysis. So sometimes what we do is, when you compare block, let's say, let's go back a little bit here. Okay, so let's say, for example, you're comparing this block here with this block here. Okay, of course, I'm going to get the mean of all the, remember we indicated that block 1 seems to be the most high yielding block, and then block 4 seems to be the low yielding block. So if I get the total or the mean for block 1, and then I get also the mean for block number 4, I get the difference. That means I'm comparing the 2 blocks. Now, when I'm comparing the 2 blocks, in incomplete block design, the thing is that the treatment that are in this block may actually not be in that block. So then it becomes a little bit difficult to separate the effect of the block from the effect of the treatment. And if you've heard people talk about non-orthogonality or orthogonality, and somebody asked some question related to orthogonality, which I tried to. So if you can distinguish, if you can actually remove the effect of the block without affecting the comparison, the effect of the treatment, then we would say the block effect and the treatment effects are orthogonal. In that case, they're independent of each other. Okay, so the comparison that we make between the block may actually carry important information about the treatment effects. So this is very, very key. The comparison that we make about a block may actually also contain information related to the treatment. So let me go back. I think I have a nice, I can go back to this, and then okay, let me clean up a little bit. Okay. So remember, we indicated one thing here, that here we seems to see an increase. In block 1, we seems to be an increase in yield as you increase the amount of fertilizer. Okay. Here we seems to see an increase, and then at some point the thing reduces. Okay. So if we are comparing this block here with this block here, okay, there's going to be the fact that this block seems to be more fertile compared to this particular block. But there's also the issue that there seems to be some leveling up in this block that doesn't appear to be in that. So the issue here is that this other treatment 4 and 5 seems to have bigger effects in block number 1 compared to block number 3. So that effect there now seems to be, now we are looking at the fact that the block one block is fertile compared to the other, but there also seems to be that the treatment seems to be doing something different. So we need to combine this information at the end of the day and then see how we can use that information to get a better estimate of whatever we are trying to look at. Okay, so interblock analysis utilizes information on block effect, at least not removing the interblock in estimating. So what we want is therefore that we want to first compare the block information between the different blocks without removing the treatment information in estimating the treatment effect when you are conducting analysis. So we want to see, can we also get that information that's related to the differences between the block and then try to include it into our analysis. So this is achieved through what we call interblock analysis of incomplete block design. And in this case, the key thing here is that the block effect will be considered to be random. In the case of intra-block, the block effect was considered to be fixed. Now, this assumption is completely going to change the way we look at things, how you're going to do the estimation of the mean, or how you're going to do the estimation of the variance. Okay. So we looked at two analyses now. We looked at intra-block analysis, and then we also looked at the interblock analysis. So what happens here is then that when it comes to recovery of interblock information, we are trying to combine both the intra-block and the interblock analysis information. We are trying to use this information. We pull the information together and then use the two estimates to obtain probably a better statistics than what we would do if you had only done the intra or the inter. And precisely that's the whole idea with interblock recovery. So we know that the interblock analysis estimate treatment effect based on the treatment information within the block. And that's why we call it intra. We are making comparison within the block. What's the difference between A and B in block 1? What's the difference between A and C in block 2, in block 3, in block 4? But with the incomplete block design, the challenge is that A and B may not occur together in a number of blocks. So then in that case, then you cannot compare them in all the blocks. You only compare them in certain number of blocks. Then the issue that I talked about is what we call, I talked about the non-orthogonality. So with the incomplete block design, there is non-orthogonality since not all treatment appear in a block. So we can have treatment A and treatment B not appearing together in any of the block. Okay, so the effect of the block may become difficult actually to remove the effect of the block from the comparison of the different treatment, and that's why we say this is an orthogonal design. So the first person to talk about recovering of information from interblock information was Yates in 1940. And since then, we really move on. A lot has been done. This is going to be the last few slides, and then we'll call it a good day. We need to release you people early so that you go for Valentine. We don't want to be blamed for failed relationship, but hopefully things will be okay. Don't worry if the things break up, you have knowledge. You get more money, and then you'll also be able to start another one. Okay. So what I want to do here is we have two blocks here. We have block 1 and block 2. So if you see from here, block 1 and block 2, they all have, so we can compare A okay, so there is A in block 1 and A in block 2. There is D in block 1 and then D in block there's D in block 1 and D in block 2. So if you're comparing block 1 and block 2, this information is not going to be very helpful. Okay, so you realize from here that actually when you're comparing block 1 and block 2, you're actually comparing also treatment B and treatment E. So you cannot separate now the comparison between treatment B, okay? Because remember here, treatment B occur only in block 1, and then treatment E occur only in block 2. So if you're going to compare the total for block A, block 1 with the total for block 2, you're going to have a problem is that B does not occur in block 2, and then E does not occur in block 1. So the difference between block 1 and block 2 also have information relating to the difference between B and E. And this is actually what we call as, this is actually what we have as interblock information that we need to recover and then combine it with the intrablock information to get a better estimate. Okay. So the main objective of recovery of interblock information is to recover the interblock information and combine it with intrablock information so that we have a better estimate than you would have if you only deal with the intrablock. Okay. What I want to emphasize here is just this, that if blocking is effective, that is, if your blocks are very okay, they are different in terms of their effect on the the variable of interest, then the interblock estimate contribute very small amount of information. So in that case, the use of fixed effect block as a fixed effect would be enough to actually do your analysis. So you will not have any problem as far as that is concerned. However, if blocking is not very effective, then the interblock information actually will be substantial. So you need then to decide when you can use intrablock, when you can actually use the recovered information from the interblock information and use it into your estimate to make your estimate much better. So that is the whole thing. And then just now a few slides just to show some results, and then we call it a day. Okay. So here, the first example here that we are going to run tomorrow morning is we're looking at balanced incomplete block design. So with balanced incomplete block design, what we indicated the other day was that each pair of treatment occur together in a block equal number of times. So if you look at 1 and 2, so 1 and 2 occur together in block 1, occur together in block 2. Is there any other block? So they will occur 2 times. So if you look at 2 and 3, they are occurring together once. They are occurring together maybe here also. Okay. So here we have blocks. There are 10 blocks, block 1 up to block 10, and each block only has three plots if it is in the field. So here 10 blocks, each block has 3 plots. So K, which is the number of units within a block, is equal to 3, and each pair of treatment occurring together equal number of time, which is 2 times. And that is what we call our lambda when we are talking about balanced incomplete block design. So this is one of the data sets that I picked from somewhere, and then we're just going to analyze it to show. So the first thing that I always do, I need to look at my statistic. So from here, descriptive, yes. So here you can see that variety 1 seems to be doing better than the other variety, slightly better than variety. Variety 3 is very noisy. There's a lot of variation in variety 3 compared to the rest. And yeah, so you can see. So I will not be surprised if the interaction is, if the varieties are not different from each other. I will not be surprised. But you also need to look at the effect of the block. So when you come here, you find there are blocks that actually have, there is less variation in a block. These blocks here have very little variation. There are blocks here. This block number 2 is the okay. So this block completely has a lot of variability in it. So the assumptions of analysis of variance that the variation within the block should be similar may be in trouble here. Okay. This is when you look at the variety, but the different blocks. Now, remember, block 1 only has variety 1 and variety 2, 1, 2, 3. Then this one have. So this is just to show it's not a clear box plot. Now, so because this is where we look at the intra-block. So remember, I said intra-blocks is when the block effect, we consider the block effect as fixed. Okay. So we just run the same model as we run analysis of variance model. Okay. We have here yield being explained by block and variety. Then our data is the data that we call BIB data. Okay. But the difference now comes in here. Now here we say drop 1. Fit yield model, which is what we have actually, what's the result that we have here. And then we say test equals to F. So this one provides for us what we call type 3 sums of squares. There's type 1 sums of squares, there's type 2 sums of squares, and then type 3 sums of squares. Remember, we indicated that with the intra-block analysis, what we are trying to do in this case, we are trying to first remove the effect of the block before we look at the effect of the treatment. So the type 3 sums of squares is the one that will give us that. It calculates the treatment sums of squares on condition that the block effect has already been removed. And this will give us this kind of result. So here, well, we can see the blocks are not significantly different, but the treatments are significantly different. So we got it there. So the type 3 sums of squares, block effects removed before estimating the treatment effect. That is, the treatment effect is removed from the leftover. That's what you have there. And then you can also use, for the intra-block now, we change and we use the mixed model. So this is the mixed model approach. Now, mixed model results sometimes comes in a weird way. I mean, if you're not used to it, you're used to the ordinary analysis of variance, you may not actually be able to tell what is going on. So here, we like any model, you need the response variable, which is yield. And then we need our variables, the explanatory variable. So variety here, we can see is written without any alteration. But when it comes to the block, they have a bracket here, they put a 1, and then they put here. So this one here is telling you that please consider this effect as random. And then consider this as fixed. And then you run as that, okay? So then here the output will start coming. It tells you that, okay, a linear mixed model fitted with Remo, okay? That's what it tells you. This is what you've done. It tells you that this is the model that you've fitted. And then it tells you that the Remo criteria at convergence was that. The random effect, you see now the block is the random effect, okay? And then residual is also a random effect. I'm going to talk about this under mixed model. Then it also tells you when we come to the fixed effect. Okay, so when it comes to a fixed effect, then it kind of gives you a result that is, I mean, if we are used to analysis of variance, you're probably better off with this. So this is part of the information that you can get. So here it tells you that variety, this is the sums of squares for variety. We all know about sums of squares. This is the mean sums of squares. This is the numerator degrees of freedom, which is 5. And then this is denominator degrees of freedom. Now, it's strange a bit here that the degrees of freedom is actually not is as decimal place because they are estimated. And then it gives you, this is our F, and then it gives you this F value, and then it gives you your F statistic. So here you say, well, the treatments are significantly different. We have estimated the block effect, and then we have estimated the residual. Now, in this case, we don't test for the block effect. We only test for the variability between the blocks. So here you can see that the variability between the different plots is almost half of the variability of what we call experimental error variance. So this is how your LME runs a Remo and produce for you a result. And this result is actually acceptable. These days, if you talk about mixed model, people may actually consider you're being more sophisticated than an old person who talks about analysis of variance all the time. You can also do the same analysis using what we call BIB.test. So BIB.test can also be used to give you the same thing. You run it here, and then, so what I put in red is the command that you have the script with you. I will ask you to run it overnight, so that tomorrow in the morning, you're just going to tell us which one ran successfully and which one failed. Please, when you're running R, please don't give up. R can be very stubborn. It can always tease you a lot, but you just have to fight on until you get what you're looking for. So here it has the output here this output that we get, what I call out.bib. It has different parameters. So it has what we call the parameters. So it shows you the parameters of the balancing complete block design. Say lambda is 2. Lambda, remember, lambda is the number of time each pair of treatment occur together in a block. It tells you that the treatment, there are 6 treatments. It tells you that there are 3 blocks. No, there are 10 blocks. The lambda treatment block size, it's a bit mixed up here. So we need to push this one a little bit on this side. Okay. Then it tells you about the mean, the overall mean of the experiment. It tells you about the efficiency of BIB compared to RCBD, and it tells you coefficient of variation that you have there. It can also generate for you a table with the letters showing which ones are significantly different from or different or not. One thing that I would like to really make you know is that there are so many ways of doing the same thing in R. So you only need to get your way around. If you try one particular method, it doesn't work, you can look for another method and also try that one there. But the whole idea is you have to persist. If you are the ones who give up very easily, you're not going to learn R. So no matter how many times you get the red, please continue running. You just assume it's Valentine's Day, and then the red is good, and you go on. Okay. So it also gives you the mean. So now I want to just show this. You see, this is the mean, the original mean that we from our data, and this is the adjusted mean. So this is the mean that is got after the effect of the block has been removed. And as you see from here, the standard error is always the same in BIB because you have equal number of replication. Each pair of treatment is comes together equal number of time in each block. So the number of replications are actually the same. And finally, not the final slide, but the final things I'm going to talk about. The final design that we talked about, and this one is very, very famous with plant breeders. Somehow I got adopted. I became a plant breeder by association because I shared with them. But I've never done what the bees even do of just getting pollen from one and putting it onto the other. Okay, so we are going to have a data set which is called John Alpha. And that data set comes from a package called AgriDat. So AgriDat is a package in R that has a lot of data sets that are related to agriculture. And if you want data set to practice, you can go for that particular package. So the first thing that you need to install the package. You need to call the package before you start using it. Okay. I also save this data as johnots.csv you have it in the folder that you've given you. So if you fail to get it from the website, you can actually run it. I already gave you this one here. So I picked this example that I'm going to show you. I picked it from this website, so it's not really my original work. If you want to know more about the data itself, but first make sure you have the package installed and you call it. Just type question mark and say john.alpha, you enter, it will give you information relating to this particular data set. Of course, you always have to start with the running a box plot. So here you can see that there is a particular variety here that seems to have the same value, maybe very little variation, and there is this one here that is highly variable. Now, highly variable varieties are associated with stability. They are less stable compared to the ones that actually have a lower variation. Of course, stability will also, you want a stable variety, but what is a stable variety? If you have a variety that yields 0 kilogram per hectare everywhere, that's very stable, but is that useful? That may not actually be the case. So if you look at the different replicate that we have, remember alpha lattice design is a resolvable design. That means you can group your subplot into your blocks. They are smaller blocks. You can put them into a super block that will create a complete replicate. So from here you can see that replicate number 3 seems to be having a lower yield compared to the other one, but it also seems to have less variability that you have. And then if you look at the blocks, so we seems to have block number 6 with a lot more variability. We have here less variability. The yield for the different blocks are similar. So from here, probably you can also tell whether actually there's need for blocking, because if the blocks have similar means, so there probably no need for blocking in this case. And the good thing with the alpha lattice design is that if you find out that there is no need for blocking, then you go and run your analysis as RCBD. You collapse the blocks into your replicates, and things will be okay. So this is how you can, so what we can do, we can actually run this as our RCBD. We ignore the block. assume that we have 3 replications. Once so here you have, now this is completely now set up in completely different. You have not seen. Oh, you're saying it is too much. Just let me talk until the end. That's okay. I will start from there tomorrow. If I stop talking now, it's going to be harmful to my health. No, this is the last few slides now. We're okay. Okay. So what I want to show here is that sometimes you can actually see a strange way of how a model is written. Like this one, for example, start with a 0. Okay. So it's going to be like you try to go and read a little bit and see what you come. So when we run this is our normal analysis of variance with a complete randomized design. So here you see that the genotypes are significant. The replicates are also significant. You can run this with blocks as fixed, but in this case now we are not running it as RCBD, but running it as incomplete block design. But this case now we are looking at the type 3 sums of squares, and we still get significant replicates, significant block, and so on and so forth. And then you can also run it as a mixed model, and then you get these results here. So finally, you can compare the different means that are estimated. So we'll now talk about this, the last slide. So thank you very much. I'm sorry for pushing you a little bit too hard, but sometimes it's necessary. So if there are any burning issues in the chat that my colleague thinks I can address, but I think I think we can start tomorrow. Okay. 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 No, I'll redo part of this tomorrow with the analysis itself, so that we should be able to sort it out. Don't worry if you've not got anything for now. We'll sort it out tomorrow. At least tomorrow you start from somewhere, from 0 rather than from negative. Okay, thank you. See you tomorrow.